So, we are almost at the end of our school, so this is our last Yaga school day, and yeah, this will be a little similar to yesterday, but this made also with practicals and better notebooks. And first of all, I want to introduce you to our lecturer, Alexander Grayver from the University of Cologne. His focus is mostly on geomagnetism, right?
Right.
And he received also a Heisenberg grant on the Science Foundation in Germany. And yeah, today then he was at the ETH Zurich as well. And used to be also at GeoSat and
Germany, all over the place.
Yeah, so many places.
Yeah.
And today he will tell us about electromagnetic induction methods in geophysics, implications, and theory. And as we already heard from Chris yesterday, there is also a common paper with the model of the ocean tides in this field. So, and all of them are still here and will interact.
Okay, thank you, Barbara. And, it's my pleasure to welcome you to this lecture today. It's the last day. I hope you still have a bit of energy to keep up, you know, for a few hours. And let's see how it goes. Maybe we also managed to finish a little earlier today. Yeah? So I appreciate it's been an intense week for you. Yeah, full of new knowledge. And new, perhaps, contacts, new experience. Indeed, so we're going to be talking about electromagnetic induction methods in geophysics, theory and applications. And normally this would be a full course, yeah? And so today I had to really squeeze it in, so we will not cover everything, and I will frame the context of today's lecture a bit later. I mean, more on the organization part, so you are well aware by now what IAGA is, and it has a few divisions, and there is a division 6 called electromagnetic induction in Earth and planetary bodies, and so the context of this lecture, today's topic, relates a lot to our activities in this division. So I've structured today's tutorial and lecture in the following way. We will have two parts, basically split by the lunch break, and then with some coffee breaks in the morning, in the afternoon. And these are roughly some bullet points, topics that we will cover. Yeah, so we will have actually first practical before lunch, and then the second practical in the afternoon when we conclude today's IAGA school. Let's see how it goes. And again, as I said, I appreciate it's been very intense for you. So the principle for today, less is more. So I will try not to load you too much, but give you some kind of outlines and highlights and resources maybe that you could use later to dive into this exciting topic if you carry this interest beyond this lecture, which I hope you will. And again, I also want to appreciate and acknowledge a lot of colleagues whose materials, one way or the other, over the years, I've been using, modifying, and I want to say thanks to many of them for making their materials available. We will start with a few kind of literature highlights. By the way, these slides are on the Google Drive, so in case you want to get them. There are two versions, because my presentation was 1 gigabyte, and when I was converting it to PDF, it was like 200 megabyte PDF, and then I created a smaller version in case you cannot open the large one. Anyway, so electromagnetic methods are very diverse, and basically you can apply them at very many different scales. If you're interested more in applied and near surface part of the solid Earth, you might find this literature useful, and by applied at near surface, we typically relate to depth which you can drill, so first few kilometers. Then we have actually 3 books on the magnetotelluric method. So magnetotelluric method is perhaps the most popular method among different electromagnetic induction methods. So we have 3 different books which you also might find useful. Then there is this very comprehensive chapter written by Steve Constable for the Treatise on Geophysics, and it covers a lot of topics which are not covered in any other book. I mean, it discusses instrumentation, and also satellite observations in the context of electromagnetic induction. It discusses rock properties. Most importantly for electromagnetic induction is electrical conductivity. So this chapter is really a very good source of initial sort of knowledge in this field. And then in the context of IAGA activities, we also hold biannual meetings. They are called Electromagnetic Induction Workshop. And after each workshop, we have a tradition to publish review papers on some selected topics. And these are the review papers on the large-scale electromagnetic induction studies for Earth and the extraterrestrial bodies. And the last review paper was actually published by myself just last year. So this is also a source of information for more large-scale studies, deep studies, also not necessarily confined to Earth. There is also this very popular resource. It's called GeoSci, and in fact, we will be using some of the materials from this resource in the first practical today. It covers mostly the applied and near-surface geophysics, targeting the applications which are listed here. And that's also good because I want to give you sort of now a bit of motivation why electromagnetic induction methods are useful. And here you see a good kind of summary, a good collection of actual applied topics that you can address with electromagnetic induction methods. But you can do much more with them. So the physical property that we target is electrical conductivity of the subsurface. We try to retrieve the distribution of electrical conductivity. It can inform us on many fundamental processes that happen in the subsurface. For instance, we can image volcanic systems on the left. We can image melt transport along the mid-oceanic ridges. We can image the asthenospheric processes, the so-called lithospheric delamination under the central Mongolia, as is an example here. We can also image some transform faults in the subduction zone. So this is a subduction, and you can see there's some variations in conductivity here that are related to the faulting systems in this region. We can also image very complex groundwater systems, the saline and freshwater reservoirs, as is an example from the Dead Sea region here. In fact, I myself specialize more on a large-scale induction, and what I will be presenting at the following meeting, at the IAGA meeting, are 2 examples of very large continental scale imaging that we are also capable of doing these days. So this is an example for US, and this is an example for Australia. So if you're interested, you're also welcome to attend these presentations on Monday. So what are the methods that allow us to do all this exciting research and applied research and fundamental research? This is a table that I've compiled and modified after Constable 2023, and it lists some of the main methods that we have with some very brief description and the mode of operation. What I mean by mode of operation here is whether these methods are operated in an active regime or in a passive regime. Active means that we generate some signals, electromagnetic signals or currents, and we inject them in the subsurface, or we generate them within the subsurface, and then we measure the response, so that be active. And the passive means that we rely on some natural processes. So we have methods that are based on the direct current, such as DC resistivity or electric resistivity tomography, which is an active method, and it targets electrical conductivity as a property. We also have self-potential method that also uses DC electric fields, so the direct current, stationary current, and it can be used to image the water resources and some minerals in the subsurface. We also have induced polarization methods that are targeting the stored charge and in the subsurface, and they are also very common in mineral prospection, in clay characterization, and other things. We have controlled source methods where we generate electric or magnetic fields, or more electric currents or magnetic fields, and we measure the response, and again we can infer the electrical conductivity. We have ground penetrating radar, which sometimes is referred to as a seismic method, but it's not. But it uses wave phenomena, so it uses electromagnetic waves, so in a very, very high frequency regime, and it can be used to do very detailed imaging of the very near surface part of the Earth. And then finally, we have a set of passive methods that are based on electromagnetic induction. And this is, in fact, the focus of today's lecture. I'm going to be covering the magnetotelluric method, the geomagnetic depth sounding, and also something new. I heard you already learned about it a little bit from Chris, the fact that we can use natural oceanic currents to study the subsurface conductivity. This is something new. You cannot find it in any book yet. So, and we will be talking about this today. So a little bit more details about these passive electromagnetic methods that we will be covering. So you see here a table. You see the method on the left, and then you see what source of natural electromagnetic variations or currents we are using. You see the typical frequency or period band these methods operate within, and then the typical depth range. I mean, this is all a little bit approximate, so just to give you an idea. And this is how we can acquire data within these methodologies. So either we can do local or regional surveys, so installing temporary stations and moving them around. We can also use ground observatories or satellites. And you can see here, basically, what is very important to note here is that we have a very, very broad period band available to us. So we can use natural electromagnetic variations in the millihertz range and image up to a few hours and image the lithospheric depth, so from approximately very near surface to a few hundred kilometers. Or we can go for very long periodic variations generated within the magnetospheric field, magnetospheric ring current, and we can sound much deeper into the Earth. So this is what makes this electromagnetic induction method so powerful and useful for Earth and planetary studies. So the principle that is common to all these methods, I've tried to sketch it here. So what you see is a section of the solid Earth, and there's really, it's not to scale. Yeah, I mean the solid part of the core is much bigger than it should be. And everything is, actually it's not to scale, so don't pay attention to scale, yeah? But it lists the main layers here. And what it also shows are some primary current systems that we have in the ionosphere, in the magnetosphere higher up, and of course they connect in the polar regions, sometimes also at mid-latitudes. And also we have some currents generated within the ocean. So these are our sources. And what we measure in this, with electromagnetic methods, we measure the Earth's response to a time and space varying electromagnetic source field. So it goes this way. So we have some primary currents which generate primary magnetic fields. Yeah? So these time-varying currents, they generate time-varying magnetic fields. And these primary magnetic fields, they generate secondary electric currents within the conductive part of the solid Earth. Yeah? And these secondary currents generate secondary magnetic fields. And so this happens so all the time. Yeah? So we will cover the physics of that later. And what we measure with satellites, with observatories, we can also install instruments on the seafloor or fly them on an airborne platform. We measure this time-varying, a superposition of these primary and secondary magnetic fields and sometimes also electric fields. So a typical workflow for us would be then to, as I said, measure this time series at some location on the ground, on the seafloor, or above the ground. And then we would process our data, and the processing is highly specific depending on the method that you're using. So what we do for instance, tidal magnetic signals versus what we do for magnetotellurics is rather different. But in any way, in any case, regardless of the method you are using, so we are processing this data. I mean, we are trying to minimize the noise, remove some outliers and other unwanted effects. So very standard thing. And then we often stack our data. So again, to get a more reliable estimates of the responses measured. And then we would fit this data into what we call an inversion. Yeah? So we would fit this data into inversion, and this inversion needs one more piece. It needs a description of the physics. It needs some part that tells us how these electric and magnetic fields depend and vary with primary currents and with the distribution of subsurface electrical conductivity. This is what we would call a forward operator. We will talk more about it, so this is just a very simple sketch. And our ultimate goal is to get a distribution of electrical conductivity, which we denote by sigma, and then we would interpret this conductivity using also some additional information that we can derive from geology, from tectonics, from other geophysical properties such as seismic properties, and many, many other possible sources of prior information that we can use. We have to use this prior information because electrical conductivity alone is often not enough. So it's not a unique indicator of some process or material in the subsurface. So we often have to look at other evidence to provide new insights. So now a little more information on what types of data we use. So as I already said, we can use ground, satellite observations. And basically, we have this network of geomagnetic observatories, which IAGA has a lot to do with. They are operated by different institutions in different countries, and the advantages of this data source for us is that these are long and quality controlled time series. And the major limitation with ground observatories is the fact that they are rather sparse in many parts of the world. I mean, primarily over the oceans and in the southern hemisphere. Still, it's a very important source of observations. We also have a possibility to install temporary stations, so we can take a magnetometer or electrodes to measure electric fields, and we can go to different places and measure the natural electromagnetic variations. And this has been done for many decades, and some of the recent highlights are these national-wide electromagnetic arrays such as AUSLAMP or MT-US array, and they provide us with really unprecedented coverage and resolution for electromagnetic induction studies. These surveys take years, so MT-US array has actually been completed last year, and it took 18 years to sort of have a few dozen of stations, and each station has been installed for 1 month, and they have been moving these few dozen of stations and measuring 1 month and moving them further. UK has done a similar work recently, and naturally for UK it was a little easier because it's a smaller country, yeah? So it's easier to cover. Sorry?
It still took 4 years.
Yeah, it still took 4 years. So this is a big effort, big multi-institutional effort. And the fact also that this data are often made public is a huge advantage for our community. Last but not least are, of course, satellites. So we have ESA swarm satellites, which you are by now aware of. And this is really, I think, Europe can be proud of leading such mission. It has really pushed our community to the next level. And it's extremely accurate. It delivers us with extremely accurate data with a good coverage. There are some limitations which we have with satellites, and that is that there is some space-time trade-off. You know, satellite is here, it measures, and then it moves immediately here, and so it's moving all the time, and we need to deal with these complications. And what helps us dealing with these complications are actually more satellites. So the more satellites, the more simultaneous measurements we have, the better our instantaneous coverage is. And we are very fortunate to have, next to Swarm, to also have missions such as MSS, or Macau Space Science Satellite, and also ESA is leading an upcoming NanoMaxSat mission. We also have many the so-called satellite platform magnetometers, which are installed for the purposes of navigation and attitude correction on many satellites, and some of these platform magnetometers are good enough to do science with them. So this is a bit about the data that we are using for electromagnetic induction studies. Let's now dive into history and look very briefly what were the major milestones that led us to our current state. It didn't start in earth sciences or geophysics, it started in physics, of course. Electromagnetic induction, the phenomenon of electromagnetism has been studied for centuries. It started around the second half of the 18th century, where, for instance, Coulomb has developed an apparatus that allowed him to establish his famous law that carries his name. That was around 1785. And then in the following few decades, the Volta invents the battery, the so-called voltaic pile, and the Gauss generalizes the Coulomb's law using his back then new flux theorem. And Ørsted also observes that electric currents deflect magnets. And shortly after that, the Ampere, he actually made a more detailed study following the Ørsted observations, and also noted that a wire, a metallic wire that carries a current, it exerts some force on a second current carrying wire, and he noted that a coil then behaves like a magnetic dipole. And a decade later, Michael Faraday, he establishes the fact that that makes current from a moving magnet, and that is the famous electromagnetic Faraday's law of electromagnetic induction. And what is also interesting is that it was Faraday who also thought about natural electromagnetism a lot. Among other things, he predicted that a water, which is mildly electrically conductive, as it moves through the Earth's magnetic field, it would generate an electric field, an electric current. And that prediction was made many, many decades before this phenomenon can be observed. And we will talk about very modern observations of this phenomenon later. Then finally, in the second half of 19th century, James Clerk Maxwell, he recognized that many of these phenomena, they can be combined into one theory that he also complemented with a few additional terms, and eventually this has formed the theory of electromagnetism as we know it today. And in fact, a somewhat interesting thing is that it was Olivier Heaviside that actually formulated the Maxwell's equations in the contemporary form using this nabla operator and vector calculus. We will see these equations later. If you want to learn more about the history of electromagnetism, there is really an excellent book which I highly recommend you if you are interested in the history of science. And then there was a parallel line, so there was a phenomenon of electromagnetic induction that was observed more in geophysics, or some of the milestones that were particularly important for geophysics, and that is, of course, the work of Carl Friedrich Gauss, who developed the spherical harmonic expansion, the potential representation for the magnetic field that allows the separation of the external and internal fields. And also around mid-19th century, the observations of natural electric and magnetic fields had become more common, including the fact that they were, that people noted that actually there are some disruptions during some periods in the telegraph cables, and that was largely, I think, among the first observations that you can refer to as space weather. Yeah, and these disruptions observed by Clement, they were related to the famous Carrington event, the strongest geomagnetic storm that had been recorded and observed. Then Greenwich Observatory started observations on electric potentials in 1865, and finally, at the end of the 19th century, we have the first electromagnetic induction sounding work that was done by the Arthur Schuster, who used the Gauss separation method, who used also the observations of the magnetic fields on the surface, and the theory of electromagnetism, the Maxwell's equations, and combined all that to infer some information about electrical conductivity in the subsurface. So he concluded that there is a strong evidence that the average conductivity is very small near the surface, but must be greater further down. And as you will see on the next slide, this was a correct prediction. So this is basically the birth of electromagnetic induction sounding. Then this has been picked up by many other prominent scientists at the beginning of 20th century, in the first half of 20th century, and the theory was elaborated. There were more observations to use, and then then the first conductivity profiles, the 1D conductivity profiles, were derived. So, for instance, this is the model by Lahiri and Price from 1939. And you indeed see this trend. This is the depth, this is electrical conductivity, and you can see electrical conductivity increases with depth. So this kind of corroborates the Schuster's first prediction about that. And there are some other profiles here which were derived by other scientists using slightly different methodologies. One of the very important milestones around the mid of the 20th century was the invention of the magnetotelluric method, initially by some former Soviet scientists, Tikhonov and Japanese colleagues, and later by Louis Cagnard, who actually gave the name to the method. Right. And finally, just some very few notes on the very modern developments. So in the 80s and 90s, we have seen an advent of, I mean, if you noticed, yeah, I mean, many of these previous studies, they derived 1D profiles, so just conductivity as a function of depth, either globally or just at one particular location. And in the 80s and 90s, this concept has changed, and so with more computational power and with more observations, we could start doing the 3D modelings and 3D interpretations, so deriving these volumetric models that we are used to now, and some of them I've shown to you. And at the beginning of the 20th century, we start having like continuous satellite measurements, magnetic field measurements that also enable electromagnetic sounding with satellite data, still just 1D. And in the 2010s, so in the past decade, in the previous decade, we also have seen the first 3D global conductivity models using the ground observations. But they still rely on a very old methodology, which will be the topic of our second practical today. So you will see how this method is implemented and try it yourself. Then approximately 10 years ago, we managed to show that also the fields generated, the currents generated within the ocean, they generate secondary currents and magnetic fields in the subsurface that can be observed at satellites and can be used to probe the conductivity of the mantle. And finally, also, now we have this unique continental scale electromagnetic arrays, and we can study the 3D conductivity on a continental scale. What we cannot do yet, and this is one of the key sort of challenges in our community, is that we do not have any coherent multi-scale global 3D model of the Earth electrical conductivity. We still don't know how it looks like on a global scale. You probably have seen these kind of seismic tomography models, you know, imaging subduction zones, plumes, many other mid-oceanic ridges on a global scale. We do not have something like that for electrical conductivity. That is still a knowledge gap. We are still working on that, and hopefully one day it will be solved. Right, so let's talk a little bit more about the Earth electromagnetic environment. So what generates these currents and primary magnetic fields that we are using as a source for electromagnetic induction sounding. I don't know, have you seen this figure this week? Yeah. Okay, actually, yeah, maybe I can just skip all that, you know, or just go very quickly, yeah. Yeah, I guess this figure will yeah, you will probably see it more times in the future. Yeah, I think it's a great figure that summarizes yeah the shows the fact that magnetic field is such a unique thing, you know, that it varies on all time scales. Yeah? But there is some clear separation, so into fields of internal origin and fields of external origin. Yeah? The period band or the frequency band that we are interested in for electromagnetic induction studies is, or at least for the ones that we cover in this lecture, is this period band. Yeah, so it roughly for the longest periods it goes from the 11 years, so from the solar cycle. This we think is the longest natural time varying harmonic signal that exists, yeah? At least the one of external origins that is driven by the sun, by the activity of the sun. And then it goes all the way to the microsecond range, where the signals are generated by mostly atmospheric phenomena and some irregularities in the ionosphere. We'll talk about that more. Yeah, so these are the sources of magnetic field that we are using. So if we then write a magnetic field at some location as a function of time, we can, for the purposes again of electromagnetic induction, we can decompose it into several parts. We can represent the largest part denoted with B core, and again, if we look only at these scales, yeah, the largest part of this core field can be considered as a constant component. Yeah, so then there is the lithospheric or crustal part that is much smaller and that is also constant. And then these core and lithospheric fields, they of course we know they vary in time. Yeah, so they are not constant. They vary in time also at the periods that we target here, and this is partially a challenge for us. I mean, how do we separate the parts of the signals that come from the core from the parts of the signals that come from the mantle? But that's a slightly different story. And then we have also the part that is generated by the ionosphere, magnetosphere, or oceanic tides. They vary in magnitude, somewhere between just a few nanotesla to a few hundred nanotesla. And these are the signals of our interest. Yeah? Yeah. Again, how it looks in data. So let's look first at 50 years of magnetic field time series here from the Hermanus Observatory. So you see X, Y, and Z components, and of course, I mean, these very slow trends there are due to the secular variation that come from the core. So let's zoom now and look at 1 year of data at the same observatory, and now you see a lot more short-term dynamics here, including, for instance, this sequence of very, sharp peaks that represent the magnetic signature of geomagnetic storms. I think what is quite unique here is the fact that there were 4 storms sort of happening in sequence around that time. So this is not due to the core. This is due to some external processes. Again, let's zoom, and now we have a time series of 1 month, and we can look more into these magnetic storms. So we have, again, you have had a lecture on magnetosphere, so I assume that a lot of this is already familiar to you. So there are different phases of this geomagnetic storm, so at least the way we see them in magnetic field observations. So we differentiate between onset of the storm or commencement of the storm, the main phase, and then a much slower recovery phase. But there are also other signals which in this case are very clearly visible in the Y component. So this is the east component of the magnetic field, and these have a very clear diurnal periodicity. Yeah, so this is also something you probably know by now. Is a skew current system. Yeah, that originates from the E region, from the E layer in the ionosphere. So these variations that we see here, they are driven by the external currents in the ionosphere and magnetosphere, but some part of this variation is also due to the currents that have been induced in the subsurface by these external sources. So what we observe here is a superposition of these external fields and the induced fields. Yeah? So it would not be correct to refer to them as a signals of purely external origin. Yeah? It's a superposition of external and induced components. So when we talk about very long period, deep electromagnetic sounding, then one of the major sources there is the magnetospheric ring current that has a distance located at the distance of a few Earth radii to a 10 or even few tens of Earth radii, depending on how you define the magnetospheric ring current. What makes it very useful for electromagnetic induction studies is the fact that it has a relatively simple geometry. So the magnetic field that is generated by the ring current can be to first order approximated as a uniform magnetic field on the Earth surface. So we can work with such geometry relatively easy. Yeah, again, the origin are the drift of charged particles in magnetosphere, plus the modulation of this drift by the solar wind, and the periods at which these variations mainly occur, at least the ones that we can observe on the surface, are between 2 days and 1 year approximately. Yeah? And this allows us to sound the electrical conductivity within this depth range of approximately 400 to maybe 2,000 kilometers. Yeah, this is how the radial magnetic field component of the magnetospheric field on the ground looks like. This is taken from the comprehensive inversion model that uses swarm data to separate these different signals. So you see that to first order, this is a radial component. Yeah, so it's a field that enters from the north and sort of exits in the south, as was shown on this previous slide. Okay, so another source of electromagnetic variations is ionosphere. For instance, the skew current system in the ionosphere that originates from the E layer, approximately at altitudes between 90 and maybe 150 kilometers above the Earth. And what makes skew a bit more complicated in the context of electromagnetic induction sounding is the fact that it's much more complex in geometry than this ring current. Yeah? So as you will also be able to see here, so it's also the CI model, the comprehensive inversion model. So it's a skew current system is a local time phenomenon. Yeah, so it happens on the sun-lit part of the Earth. So you can imagine that Earth rotates underneath, and that's why in the mass body fixed frame, in the Earth fixed frame, you kind of observe this traveling magnetic field signature. And next to this daily variability related to the Earth rotation, it also has some seasonal and annual variability, because Earth has a different tilt relative to the Sun. So the ionosphere is heated differently in the winter than in the summer, depending on the hemisphere. So this gives this rather complicated source, which we also are able to use for electromagnetic induction. This was for the, yes, and what I forgot to say is that we can sound the depth between 100 and 400 kilometers using this source. Then we have a high frequency sources, which are the basis for the magnetotelluric method. So roughly the signals in the magnetic field signals in the period range between millihertz to 1000 hertz. And these originate also in the ionosphere, and driven by the auroral electrojets, some ionospheric pulsations and irregularities, but also by generated by the atmospheric phenomena such as lightning. So, for instance, there are a few prominent resonances related to this frequency band, especially at the periods less than 1 second, so the frequencies higher than 1 hertz. And these are the so-called Schumann resonances that sort of form because atmosphere is a type of a waveguide located, between the conductive Earth and the ionospheric E-layer boundary. And these resonances, yes, have some very prominent, very clear frequencies and periodicities. And I also think, like, if I scroll back to, or if I go back to this grand spectrum, I think they are also highlighted here, these Schumann resonances. Yeah. Okay, so how does it look in data? Yeah, so we looked at magnetospheric storms, their magnetic signature. We looked at a skew current system and their very characteristic daily magnetic field signature. And the signature of lightning is different. So it's very stochastic process. So you see them as some types of pulsations. This is, for instance, a single lightning strike that happened in the April 1998, and it was measured by 3 different magnetometers. And you can see also that these signals are of very small amplitude compared to other signals. So this y-axis here is in picotesla. Yeah, so picotesla is 10 to minus 12 Tesla. So nanotesla is 10 to minus 9. So picotesla is 1,000 times less. So these are very, very tiny signals. Yeah? And we are using them to sound the subsurface, to image the subsurface conductivity. Then also a small kind of summary for different ionospheric phenomena, generally referred to as pulsations. And this is also an example of the sources that generate electromagnetic signals of use for electromagnetic induction sounding. Okay, so 10:30 was the 10, not 10:30. Yeah, yeah. Okay, good. Right, so let's talk a little bit now.
It's 10 to 10 now.
It's 10 to 10, yeah, 10 to 10, yeah. I was just, yeah. Maybe questions, I don't know. Maybe let's do it a bit more interactive and have some discussion while I...
That's a question. So the sheet resonances don't penetrate particularly deeply, though, do they? They only go, so it's just higher frequency, they only go a few kilometers. Is that correct?
Exactly, that's correct. That will be, we will cover this, yeah. I mean, the depth of penetration depends on the frequency of this variation.
Are they detectable at the ocean floor, do you know?
I mean, it largely depends on the equipment that you have. I think with modern magnetic coils, you might be able to detect them, but it depends how deep is the ocean. I mean, yeah. I mean, that's one of the challenges with this marine electromagnetic induction is when you place, maybe I explain a bit the context. So when you place, and that's a bit Russian maybe at this point. So if this is the sea floor and you can place the instrument at the sea floor, then you will have potentially, you know, some kilometers of conductive seawater above. And a lot of these signals, of these high frequency signals like these ones, they will not penetrate, they will not be able to penetrate through this conductive thick ocean layer. So you'll be intrinsically limited to the period band that you are able to observe here. Because these signals, they decay exponentially, as you will see later, yeah, but I mean, the modern magnetic coils are impressively accurate. I mean, the marine, let me put it this way. So the state-of-the-art marine MT studies, they can go to 10 hertz for depth of few kilometers. So 10 hertz at the depth of few kilometers, you can pull this out. Yeah. But that depends because there's emotional noise. You know, these instruments, they move at the seafloor. There are some currents, so it also depends where you are actually in the ocean. Yeah. But yeah. Other questions, maybe from the audience?
I'm just curious about the arrays of an Australian.
Sorry, Kieran, you're of course also audience, but I meant the younger audience. Yeah, yeah, excuse me.
I'm curious about the frequencies that they studied and the range of depth of the arrays of US and Australia.
Which depth? A few hundred kilometers. Yeah, from few kilometers to 300 kilometers. Yeah, these arrays are mainly used to derive magnetotelluric responses. So you can check later with this table that we have magnetotellurics is the method that allows us to sound down to a few hundred kilometers depth. Any other questions? Yes, please.
Just a general question, because when people say, because during the geomagnetic storms, the surface stations, transmitting stations got destroyed, in the sense they were damaged. So is it because of this conductivity in the subsurface, because of the amount of current is flowing?
Geomagnetically induced current, correct.
Is it because of that?
Yes, I think so. I mean, Kieran would be an expert on that. I mean, since subsurface is electrically conductive, yeah, if you have some very powerful time-varying magnetic field, impulse, or like something that gives a very strong variation in the magnetic field, then by principle of electromagnetic induction, which we will clear in the next slides, you will generate currents in the subsurface, yeah, and these currents, they will they might leak to the power grid and damage the power grid. Yeah.
So it will be different in different solar cycles. So we have the maximum solar cycle and minimum. So it will be conductivity will be different, right?
Conductivity is the same. I mean, conductivity of the subsurface, I mean, it varies on geological time scales, yeah, but it's related to the mineral and rock itself. Yeah, so as long as you are not changing the rock, you know, it is the same. Of course, there are events like some eruptions, you know, where some material gets transported within the crust, and that modifies locally the electrical conductivity because melt is more conductive than the solid rock. So in principle, you can have very short time variations in conductivity, but as a bulk, conductivity in this kind of context is considered constant. Yeah. Yeah. Any other questions?
Like offshore sites more in danger and geomagnetic storms.
Which of those sites?
Like on the Atlantic because of the salinity of the ocean.
Yes.
Like the offshore park.
Potentially, yes. Well, yes, it's complicated in a way. But you're right in a sense that if you are close to a very prominent conductivity contrast, such as the one between land and ocean, you will generate very strong local perturbations in the magnetic field because of the kind of complex electric current flow around the coastlines. So there might be local amplifications in these geomagnetically induced currents related to the coastline. So yeah, the coastlines are usually studied a bit extra in terms of space weather hazard potential because of this very well-known kind of coastal induction effect. Yeah. Maybe I'll show you one animation later that illustrates this. But now back to, yes, let's continue, and then I think I'll manage to finish before this section before the coffee break. So principles of electromagnetic induction, you know, so far I've been referring to magnetic fields, electric fields, their variations, you know, electrical conductivity. It's a bit kind of scattered maybe, huh? So now we want to talk about physical framework, so about physical foundation that combines all that puts this all into some mathematical description. And these are the Maxwell's equations. Yeah? So the equations that govern the evolution and the variations of electric and magnetic fields in space are Maxwell's equations. These are Maxwell's equations. So there are four of them, and we will go through them in steps. So here they're stated in a very concise form, which makes them, in my opinion, extremely elegant. And if you think that everything, also all the modern technology, you know, all the signals in our notebooks, cell phones, the Wi-Fi, you know, 5G, 6G, you name it, all the transistors, everything is this, you know. This is not only this, of course, but this is really the core of it. So the importance of Maxwell's equations is, of course, goes well beyond the geophysics. So it's a set of four partial differential equations, and which have some names, such as Ampere's law, Faraday, sometimes referred to as Maxwell-Ampere's law because Maxwell modified it, Faraday's law of electromagnetic induction, Gauss' law, and maybe Chris or Kieran, they can help me. I mean, does this equation have any traditional name?
Not of a person.
Sometimes it's referred to as Gauss equation of magnetism, but probably not. No. Right. It means there are no magnetic monopoles, or among other things, it means that there are no magnetic monopoles. Yeah, this is a nice sketch, which takes some time to understand it and grasp it, but it really is, if you remember these graphics, it will really help you understand and link these equations between each other. But I'll not talk much about it now. Actually, we'll go through it in detail later. So let's decipher some of these variables here. So we have E for electric field with SI units volts per meter. We have D for electric flux with Coulomb per meter squared. We have H for, yeah, there it's a bit complicated also. There's no like common terminology, but H is in our community at least is referred to as magnetization field in amps per meter. B is actually the magnetic field, Tesla. J is the current density with units amperes per meter squared. Mu is the magnetic permeability, Henry per meter. Epsilon is electric permittivity. Sigma here is very important, the actual physical property that we target in electromagnetic induction sounding is electrical conductivity with units Siemens per meter, and Q is electric charge density with the units of Coulomb per meter cubic, so number of charges per volume. Let's elaborate this term here, this total current density. We can split it into three terms, which all add up in a superposition, sort of. The first term would be the conduction currents. The electric currents that exist because there are some free charges, and these free charges move, and the motion of free charges creates electric current. So this is what we typically refer to as conduction current, and it actually is a representation of the Ohm's law in a stationary conductor. So conduction current equals conductivity times electric field. Then we have this other term, JD. This is displacement current. It's a first-time derivative of the electric flux density. We'll talk more about it later. And then there is this other term, which is not part of the conventional set of Maxwell's equations, but we often add it to signify that there is some source of extraneous current density, for instance, the current density in the ionosphere or magnetosphere. You know? So for us, this would be a term that describes our source, one way or the other. Then we can substitute this expanded current density term into the first equation, and this will simply give us these three terms on the right-hand side. And we can further make a very reasonable assumption that holds for pretty much all earth materials, so the minerals and rocks that we have, and this is the so-called linear medium assumption, where magnetic field and magnetizing field H, they are linearly related through the magnetic permeability, and the electric flux is related to the electric field through the electric permittivity. And using this relations, we can then also substitute them into these equations and write them in this kind of alternative form. Yeah. So now we have actually we have only H and E as field variables. Yeah. Then what is very useful for us is to be able to operate these equations not in time domain but in frequency domain. So we often do this Fourier transformation, which is a very standard Fourier transformation. So electric and magnetic fields are and current density are functions of time. So we can relate them to the corresponding quantities in frequency domain by using this Fourier integral. And then we can write, I mean, if we have a derivative, dE over dt, so we need to differentiate this term once with respect to t. That would give us sort of this I omega term would go down and would become a sort of a pre-multiplying factor instead of the time derivative. So then you basically see that these equations are all the same, except where you have a time derivative term, you replace it with I omega and the corresponding quantity in the frequency domain. Here I also use tilde to differentiate between a quantity in frequency domain and a quantity in time domain is without tilde, and this is tilde. But in what follows, I will not use this, and it should be clear from the context that we are talking about frequency domain or about time domain. Yeah? Omega here is the angular frequency, 2 pi times f, and f is just is a frequency in hertz with units of hertz, and it's a reciprocal of period. Yeah, so some very basic things. Now, as I referred to earlier, this is actually not what Maxwell has written down. Yeah, so Maxwell's equations from his seminal work, A Dynamical Theory of the Electromagnetic Field, 1863, is a set of 21 equations. Yeah, 21 differential equations. And it was, and they don't look familiar to me, you know. I mean, I'm working with Maxwell's equations, and it would take me a long time trying to understand this notation, so we are really not using it any longer. Yeah. And it was Oliver Heaviside who wrote these equations in their modern form using Nabla notation, using vector calculus, as we are very accustomed to these days. And in electromagnetic induction sounding, we can do a few further approximations and simplifications. One of them is that for frequencies that we target and for temperatures that we usually have deep down, we can reasonably assume that all materials are non-polarizable, non-electrically polarizable, and they do not have permanent magnetization. At least to a point that it doesn't matter really for us whether they do. If they have a little bit, it doesn't matter. It doesn't change the electromagnetic induction that we are dealing with. So we can basically say that this mu magnetic permeability is just the free space constant, 4 pi times 10 to minus 7, and the electric permittivity is also just the one of free space. Yeah? And then we do another simplification, or it's not simplification, we go to another approximation, because we typically work with low frequencies in electromagnetic induction. There are some very near surface applied methods that work with very high frequencies, but even they do this approximation. So it's really a universal approximation in electromagnetic methods. We will notice that if you have these two terms here, this is the conduction current, this is the displacement current, remember, yeah, in frequency domain. And you can see that there is this omega epsilon term in front of E, and sigma term also in front of E here. And if you substitute frequencies that we typically deal with, and this epsilon 0 is approximately 10 to minus 12. So this is 10 to minus 12. This is smaller than 1, or not much larger than 1. And it's usually much, much smaller than electrical conductivities of rocks and minerals that we target. We will talk about conductivities. For now, just take it for granted. That means that conduction current is a lot bigger than displacement current. And so we neglect this term. So we can just cross out this term. And this gives us then only these two terms, and this is the conduction current, and this is some extraneous current that drives the electromagnetic induction. And this set of equations is called the quasi-static approximation or quasi-stationary approximation, or in fact, pre-Maxwell's equations, because what Maxwell did to this system of equations, he actually added this term. It was missing. He added it, and so we take it away again. So yeah, this is the quasi-static approximation. So all we need are Gauss, Faraday, Ampere, and Ohm's laws. So we actually go to the pre-Maxwell era in electromagnetic induction. No displacement currents, no electric polarization. And yeah, as I said, most of the Earth materials, at least in the regime we are dealing with, are linear materials, so non-polarized and have no intrinsic magnetization. And yeah, this leaves us with simplified pre-Maxwell's equation in quasi-static approximation. And there's one thing to say, that this is really an approximation. So it's not some kind of special regime like a direct current. You know, you can drive, for instance, frequency to 0, and you will go to the DC regime, to the direct current regime, and this will be not an approximation. This will be a stationary limit of Maxwell's equations. Quasi-static approximation is an approximation. It actually violates several of the physical laws. The charge is no longer conserved, and then the speed of light must be infinity, in fact, in this quasi-static approximation. And that were problems back in the 19th century that led Maxwell to realize that this theory was incomplete, and he made it complete. And so we make it incomplete again. But it turns out, in fact, it doesn't matter for us in electromagnetic sounding. You know, we're fully aware of the full theory, and where we need the full theory, we use it, but where we don't need it, we don't use it. And there is actually a nice paper that is linked to at the bottom of this slide that discusses this kind of very peculiar, yeah, historical hiccups, I would say. Okay. There are a few things I want you to take away from this lecture. You will naturally maybe forget most of it, but there are a few things I really want you to remember, and this slide is one of them. So, because it's so nice. So you can picture this whole set of 4 equations using this slide. So the process is as follows. So we have a time-varying magnetic field in first place. And this, according to the Faraday's law, a time-varying magnetic field generates electric field. So if the magnetic field is in this direction, so it generates the field in this direction. Yeah, it's actually not a right. It's a right. There is minus sign here, right? So it's in the. I tried it with right-hand side rule. It didn't work. I thought it's wrong, but I forgot this minus sign, so it's correct as it is. So it's a right-hand side with a minus sign. Then, according to the Ohm's law, if you have electric field and you have some non-zero conductivity, so some conductive medium, you will generate electric current density. So there'll be electric current flowing in a conductor in the presence of electric field that is generated by the time-varying magnetic field. Okay? And finally, according to the Ampere's law, if you have electric current density, yeah, if you have electric current density, you then again have magnetic field. So it couples back. So you see here we have primary magnetic field, you know, minus right-hand side rule, electric field and electric current, and they are in the same direction. So the current flows in the same direction as the electric field. It's actually not always the case, but for now, let's assume it is. In plasmas, that's actually not the case, for instance, but in earth materials, they are always parallel. And then if we have electric current, we have magnetic field. And this magnetic field will be in the opposite, in the direction that is opposite to the primary field. So it will try to cancel the primary field, primary magnetic field, okay? And I think this brings me really nicely to the closure with a neat small experiment I want to show you just before the coffee break. I want you to, you don't even need to picture it. We actually have it here. We have a pipe here. Yeah? It was provided by the local university, so many thanks to them. You have a pipe. I mean, there it's stated it's copper pipe. I think this is aluminum, but it's a conductor. It's electrical conductor. Yeah, so it's electrically conductive material. And we have a magnet. Now I don't know which is north and south. It doesn't matter so much. And I will throw this magnet into this pipe. And then there are 4 options. Maybe you can come up with a 5th one. I could only come up with 4 scenarios. What will happen? So the magnet just falls through with the normal gravitational acceleration g, 9.8 meters per second squared, and nothing happens. This magnet will stick to this pipe. It's a metallic pipe. Yeah? Maybe it sticks and then doesn't fall through. Magnet slows down such that eventually it moves with much slower than it would have moved otherwise. And magnet speeds up such that eventually, acceleration is larger than g. So 5th.
Is that copper pipe? It says copper.
That's aluminum.
It's aluminum, yeah.
Yeah. Mm-hmm. Opinions?
I would say it slows down because there is a magnetic field that is created in the other direction, but weaker. But I'm not sure.
Noted. Any other opinions?
You can eliminate the E. Yeah, eliminate because it's conservation of energy, right? You cannot accelerate something.
Good. D, yeah? Yeah, but you were not referring to D, you were referring to C, right? So D, we eliminate D, and that's good. I mean, I'm glad, with the explanation, let's actually try it. I should try it first. So shall we try it? It's stuck. No, it's not. No. So it's C, huh? It's C. And
Just also drop a coin or something to show.
just drop a coin. Who has a coin? Thanks, Kieran. I mean, that's also metallic, I think, huh? But is it €1 coin or €2?
€1.
It's €1. Is €1 enough? It's too big, actually. You don't have small coins. It's only big money around. So, sorry? 50 is even bigger, right? So we need to 20. Let's check 20. Oh, too much. Who has 10? Let's check 10. Yeah. You're not afraid of losing it, Kieran, right? So if we never see it, fine. I mean, maybe there's a 5th option. It just disappears. Huh? I was much faster. I hope you all agree with that. So, yeah, and I mean, of course, this magnet is smaller in diameter, right? So you can, I guess this transparent one is just also to show that that if it's not a metal, if it's not a conductor, if it's a, I mean, this is some plexiglass. I mean, it's a perfect insulator. So with the conductivity that goes basically to zero, and of course it falls through much faster. So I'm glad you were able to relate it to my previous slide where I specifically pointed out that the secondary field is in the opposite direction. So, and this phenomenon is known as a Lenz's law. Yeah? And what happens is you have the magnet with some primary field, and it's a permanent magnet. So the magnetic field of this magnet doesn't change, but it starts moving. Yeah, it moves. So for each section of this pipe, the material, I don't know even how to explain it, but it's basically a time-varying magnetic field because this magnet is moving. It's dB dt. And then, yeah, so if we have a magnetic field in this direction, then it creates a current in this direction, and then it creates the secondary magnetic field in the opposite direction, in the direction that is now opposite to these field lines, and it basically slows it down. It's also a very nice illustration of the conversion of energy, how kinetic energy converted to electromagnetic energy back to kinetic energy. Yeah, so this. And one final thing before the coffee break is the skin effect that was kind of brought up by during the question and discussion with Kieran. It's not related now to this, or not directly, yeah. So, but it's a very prominent thing that is very important for electromagnetic induction sounding. This is the fact that if the slower the variation of electromagnetic field, so the lower the frequency or the longer the period of this variation, the deeper it penetrates into the Earth. Yeah? And so and then if you have a higher frequency, yeah, shorter period, then it attenuates much earlier. So slow variations go deep, fast variations attenuate fast and don't go deep. And the other thing is that the higher the conductivity, the stronger the attenuation of EM field. So if you have the same period of variation, the same signal here and here with the same period, the one that does not encounter high conductivity will go deeper, and the one that encounters higher conductivity will attenuate faster within the region of high electrical conductivity. This is the skin effect. Yeah, we'll come back to it later. And finally, if you want to understand this much better and much deeper, I think this is the best book that is out there, in my opinion, about electromagnetism. It's a kind of a bit demotivating because it's called Introduction to Electromagnetism and it's like 700 pages, But but it's so well structured. It's a good book. Yeah, I mean, don't get kind of upset about its thickness. So it's good. I think it's good. We could make a break, and then after the break, we will talk about electrical conductivity of rocks and minerals, and then go to magnetotelluric method. Yeah. To me?
Different.
Yeah. Right, so welcome back. The thing I actually forgot to start or to ask you about is your background a little bit, yeah? Now, as we are in the middle and we are going to some more specific methodological aspects, I think it's a good time that I would learn something about your background. I mean, And in particular, how many of you are focusing on solid Earth studies? Okay, and the outer, the external environment, like ionosphere, magnetosphere. You haven't raised it.
Yeah, what thing was solid, as in like.
Sorry?
Like a rock magnetism. Is that solid Earth?
Which magnetism? I didn't.
Paleomagnetism.
Paleomagnetism. Yeah, rock magnetism. Yeah, I just didn't hear. Okay. Yeah, solid. Solid. Rocks are solid, and as long as, do you melt them? No.
I never know what to answer. If you study in the Earth's core, if you're into the solid Earth.
That's a good point. Yeah? Isn't it so? Yeah. Solid. Below the surface or outside. Maybe that's the better definition. Okay, good. So basically, the majority are finding themselves most of the time high up. Yeah? Right. Okay, electrical conductivity of rocks and minerals is the next thing I'd like to talk to you about. So you have seen this term electrical conductivity or heard it during this lecture 100 times at least. And it's denoted with sigma typically in our community. It's an intrinsic property of a material. So any material has some electrical conductivity or electrical resistivity. And it has units Siemens per meter. Here is also a photo of Werner von Siemens. And we often go back and forth between electrical conductivity and its reciprocal property, electrical resistivity, which we denote with rho. And that's the same as density typically, yeah? So we are kind of, it's a bit unfortunate there's this overlap because there's only as many Greek letters you can have, so we have to compromise sometimes. Rho is electrical resistivity. It has units ohms times meter. So on a very kind of, school level basis, electrical resistivity is defined or can be determined by measuring the resistance of a sample that has length L and cross-sectional area A. So that's the definition that most of you probably know from the school bench. And that's and R capital here is resistance, which is a ratio of voltage over current. Yeah, so and that's not the definition that is so useful if you want to understand what is really going on when we talk about electrical conductivity of rocks and minerals. We need to go one step further, one step deeper. But before we do that, why electrical conductivity or resistivity for that matter, so just we'll be switching these terms probably back and forth, don't get confused. Why it is such a useful property? Because for typical materials, for typical minerals and rocks or other substances that are very common, such as water, on Earth, the conductivity has a very big dynamic range. Yeah? So it varies over 6 orders of magnitude, maybe even more for some extreme cases. And it depends on many factors which are very important to know, such as temperature, such as composition, obviously, the pressure to a certain extent. In minerals, you also may have certain minor phases, substances in very small amounts, such as water or part of your sample, or rock. If it's deep down, it can be molten. We can have other volatiles, such as carbon, for instance, or sulfur. And all these factors, they affect electrical conductivity, and we want to know them, to understand how Earth functions and what processes and what materials are there. So yeah, we can take water as perhaps one of the most familiar substance to all of us, and you can see that depending on the temperature of the seawater, the conductivity varies, and then depending on the salinity, seawater, say, is more saline than fresh water, and then it is also 2 orders of magnitude more conductive than the fresh water. And that obviously is already clear why electrical conductivity, for instance, is such an important property in hydrogeology or in water resource characterization. We can characterize, not only map the groundwater, but also characterize its salinity. When it comes to sediments, also a big range depending on the properties of sediments, on the porosity, and what fluid you find within the pores, whether again it's a saline water or it's just void or fresh water. Mantle has a huge dynamic range in the lower mantle, high pressure, high temperature. There are specific mineral phases that might be very, very electrically conductive, as opposed to just, for instance, peridotite. It's a very common rock, yeah, at kind of at mid-mantle temperatures or at upper mantle temperatures. The peridotite varies a lot in electrical conductivity, but it's much more resistive than the minerals in the lower mantle. So again, this is all useful characteristics. Rather than using this kind of sample length over cross-section area times resistance definition of electrical conductivity or electrical resistivity, a much more insightful way to define conductivity is by using this very simple equation, just a product of 3 numbers. And again, this is one of the things I'd like you to really remember after today's lecture, that electrical conductivity is just and it's an exact equation, so it's not an approximation. It's an equation. It's a product of 3 numbers. It's a concentration of charged species, so electrons or ions in that case. It's the charge itself of this of the mobile species, so minus for electron or plus or minus depending on the type of ion you might have, and also their mobility. The mobility is defined as a drift velocity per applied electric field. So remember, if we have electric field and we have electric charge in the presence of electric field, it will move. Yeah, and so the mobility is how fast it can move in the presence of electric field. Now, in crustal and mantle minerals, we have several types of conduction mechanisms, which, I mean, they're difficult to characterize exactly, so sometimes it's a mixture of several mechanisms, as you will see later, but let's define them as these 3 groups here. So we have ionic conduction that is happening, for instance, in fluids. We have conduction that is dominated by minerals which are good conductors themselves, so which have, say, some free electrons, such as metals, as many metals do, and then you can move these electrons, they can move around and sort of create facilitate the electric current. Yeah? These minerals are, for instance, magnetite, graphite, pyrite, and then we also have a thermally activated or defect conduction. This is very similar in principle to the semiconduction mechanism. So again, here some examples of some typical materials for these different conduction mechanisms. And again, you can have the same conduction mechanism, such as ionic conduction through water, and very different conductivities depending on the composition of the amount of salt and the amount of fluid in material, for instance, in sediments. Now, yeah, good semiconductors, conductors, and then also the thermally activated conduction. So again, what is perhaps important to note here is how big the dynamic range is in Siemens per meter between these different materials. So the first conduction mechanism by means of valence electrons is the one that is typical in metals, sometimes also in semi-metals, and that is very relatively simple to explain. So, for instance, if you take copper, it will have one electron on the outer shell, and this electron is relatively easy to move. So, if you have electric field, you will sort of have this electron moving in the electric field rather easily before it hits another atom or another electron. But that's important to note that only electrons that do not take part in crystal bonding, they determine the conductivity. So, for instance, if you have sodium, again, with one electron on the outer shell, that is very easy to move. Sodium itself is a very, very good electric conductor. But if you put it next to chlorine, they will react, they'll bond, and you will form an ACl, so the salt, basically. And then the salt itself is an insulator. So because all electrons are bonded, so there's nothing, there are no charged species, no charges to move around, even if you apply very strong electric field. Yeah. The other thing is is important, and that's how exactly the material is organized, how exactly the chemical bonds, the molecular structure is. This is the same element. This is the same chemical element in two different states. Let's call it this way. So in these states, you can see that all atoms have bonds, are connected to all other atoms. And here you can see that you have these thin layers, and there are three connections here, and then there are only essentially no connection in this direction. What kind of element is it? Maybe you can guess. Carbon, exactly, yeah, carbon. So it's a diamond here, and it's a graphite here. And note how different their electrical conductivities are. So diamond is a very good resistor, doesn't conducts nearly no electric current, because then carbon has 4 electrons on the outer shell, so they are all kind of bonded here. And in this case, you have so-called weak bonds in this direction, so you can conduct current very efficiently in this direction, but not so efficiently actually in this direction. This also is a good example of the so-called anisotropy. So, like, sometimes electrical conductivity might be good in one direction and much worse in the other direction. So what it means is that it also depends on the phase, yeah, on the state of the element. Just a bit of insight again, what the electric current density really is and how it is related to the free charges. And in fact, I don't know, maybe I don't have much time to go through this, but you can later look at this yourself, and this is all you need to derive the Ohm's law. So this is, if you recognize, this is current density equals conductivity times electric field. So if you use this conductivity definition as a product of three numbers, you can actually very easily derive the Ohm's law. So this is why this definition, in my opinion, is so insightful, and it can really help you link these different phenomena. Yeah, and this is a very nice illustration showing the the motion of electric charges in the presence of electric field. Yeah, so basically this is the electric current illustrated here. Now, what I said also that conductivity depends on temperature, but depending on the conduction mechanism, whether it is by free electrons, for instance, or by ions, the conductivity may have different trend with respect to the temperature. For instance, in metals, typically in metals, the conductivity is determined by the charge, by the mass of the electron times the tau. Tau is a free path time between collisions, because there are many atoms, many electrons, and so they collide. And so the temperature in metals, it increases these so-called lattice vibrations, and it therefore affects negatively the mobility of the electrons, meaning that they will hit each other more often on a much shorter time scale, and that will increase resistivity. So basically, metals conduct current better if they are cold as opposed to when they are warm, at least most typical metals. Okay, a different conduction mechanism by means of ions, and that, of course, is the most prominent example here is the conduction in water. So water has a lot of, or if you add salt, it will dissociate into ions, and then these ions will become your charge carriers. And then the conductivity will then be proportional to how much of these charge carriers you have, so how much salt you basically dissolve in water. And their mobility will be to first order proportional to the temperature, but in a completely different way as opposed to metals. So we will see. This is an example of electrical conductivity plot of seawater, of typical seawater as a function of temperature and salinity. So salinity is how much grams per liter of salt you have, and temperature in Celsius here. So you can see that it changes from 0.1 here to a little bit over 7 Siemens per meter, so by a factor of 10 roughly, let's say. And it grows, so it grows in this direction. So basically it grows with salinity and with temperature. So you add more salt, you have more charged species, you increase concentration of these species, you increase conductivity, and mobility becomes better with temperature. But there are some other trends. If you keep increasing temperature and you change also pressure, then you may also obtain some reverse trends. So let's look at this graph here. This is an electrical conductivity of a sodium chlorine solution in water at crustal conditions. So not here, the pressures here are between 1 GPa and 2 GPa, so that's something that you find typically in the crust, so deep down. And there are 3 different concentrations, so 0.01 mole, 0.1 mole and 1 mole. The salinity of the seawater, by the way, is somewhere between 0.1 and 1 mole, just for reference. So we have here 3 groups of curves. Yeah? So this group represents highest salinity, this group represents medium salinity, and this group represents low salinity. And you can see very clearly that the salinity typically increases the conductivity for reasons that we have discussed. And then you also see some clear trend in terms of temperature. So if you start increasing temperature, you increase conductivity regardless of the salinity. Yeah? So in all salinity concentrations, salt concentrations here, you increase temperature up to a certain point. Then at a certain point, the conductivity actually starts to decrease here. And this happens for different reasons, but it doesn't decrease as much for higher pressures than for lower pressures. So you can see here that there are sort of different, so temperature, salinity, but also pressure all determine the electrical or affect the electrical conductivity of ionic solutions. Okay, the semiconduction and ionic conduction. So if you have some material that doesn't have free electrons, then you apply electric field, and you need to you can still, with electric field applied, you can still supply enough energy to move electrons from valence band to the conduction band. And this is sort of a typical mechanism for semiconductors, where the conductivity is determined as the sum of 2 terms. So one represents the density of the electrons, and the other one represents the density of these holes. And there, the concentration of the free species is proportional to the temperature. So it has this relation here, this proportionality relation. So this is what we call thermally enhanced or thermally activated conductivity. So if you heat it up, then for the same electric field, if you heat it up, you apply some electric field, and you're able to free more and more electrons. Because as you heat it up, so you start increasing the thermal variations within the lattice, and then smaller and smaller electric field is needed to just start moving these electrons around. But there also charges can be generated by some impurities, and we have, this is basically the main regime that we have in the crust and mantle. We typically have some minerals with some impurities or defects in the lattice, and this is what creates a source of free charges in the minerals. That's why minerals are conductive. And you can roughly think of these regimes as kind of 2 parts on this diagram. So if you have temperature growing here in this direction, and you have electrical conductivity growing in this direction, then if you plot the electrical conductivity, it will have this. It will need to be then a log-log plot. So it will be a straight line here in this so-called intrinsic regime, where you supply electric charges by heating up the material. But as the temperature goes down, this curve will flatten, but it will not follow this trend. Yeah, it will start flattening because here you will be conducting electric current by providing electrons from impurities. So let's look maybe at an example of how this looks like. So this is an example of electrical conductivity of olivine. olivine is a major mineral phase in the upper mantle, so it makes up 60% of the bulk volume. And if you see here, if you plot electrical conductivity, I mean, these are some experimental results. If you plot electrical conductivity of olivine, then it will have this sort of it will form this straight line on this log on this plot. It's a log plot here, and it's kind of this reverse temperature here. So here is the temperature in Kelvin, and this is the 10,000 over T in Kelvin. So it will be a straight line here. And you see that it drops very, very quickly as temperature goes to lower values. But if you add a little bit of water, 0.1 weight percent, which is approximately, 1,000 ppm, parts per million. So it's a tiny amount of water to this mineral. Then you enhance its conductivity by orders of magnitude. Yeah? So this is this extrinsic regime where you supply charges that are free to move because of the impurities, in this case, water. At these temperatures, water, of course, will not be in its fluid form. It will dissociate in hydroxyl and hydroxyl groups and hydrogen atoms. And it will be hydrogen atoms that are very easy to move around. Or actually, it's hydrogen ions. Yeah? So it's just protons moving around. And so they will be moved. You could imagine it as having a mineral matrix and hydrogen atoms sort of moving within this mineral matrix as you apply electric field. You can see that the trend, that the slope of this curve is larger than the slope of this curve. So if you would continue it, eventually these two lines, they will cross, and this line and this conduction mechanism will dominate. So this is this intrinsic conduction. Yeah, but for temperatures that are typical for the mantle, if you have a little bit of some impurity, water in this case, this is what determines your conductivity. Next to impurities, this is some crystal lattice shown here, for instance, and you can have plus and minus, and so overall the bulk charge is 0. But then suddenly you might have some impurity that creates sort of a charge anomaly. But you can also have some dislocations in the mineral, which will also destroy the charge equilibrium. You can also have some defects, like interstitial sites, some substances here, or some holes in the mineral. And so overall, on a large scale, this will allow your mineral to be electrically conductive, again, depending on how much of these impurities, dislocations, or defects you have. And the conductivity will always follow this kind of exponential relation with temperature. So this is a nice example of this point defect conduction in cobalt olivine. This is again the reciprocal temperature, log conductivity, and these are some the lab measurements in the cobalt olivine with this composition shown here. And what you can see here, that as you increase temperature, you have one conduction mechanism, but at some point you have a completely different slope. That means you have basically reached a certain point in temperature where you can activate a different conduction mechanism, so you can supply more charge carriers. And the total conductivity would then be a superposition of all these different conduction mechanisms. There's also an effect of pressure. So for those who are not maybe familiar with the solid earth physics that much, this is a typical bulk composition of the earth mantle. at least the so-called pyrolytic mantle. So this is here pressure, depth, and here is the volume fraction of these different minerals. Yeah? So you can imagine that as you go deeper here, you increase temperature, so temperature increases. This is a typical geotherm shown with a dashed line here in Kelvin. And as you increase temperature and pressure, some of these mineral phases, they undergo phase transitions. For instance, at some depth, around 410 kilometers, olivine, which constitutes 60% of the bulk volume in the upper mantle, it will turn into woodslight phase, and woodslight phase will again turn into ringwoodite phase, and then eventually they will turn into bridgemanite, ferropericlase, and some calcium perovskite in the lower mantle. So the composition of the mantle changes, and even though these are essentially, you know, the same mineral, but it will undergo this phase transition, and induced by temperature and pressure, and this will change conductivity. So this is the lab-based conductivity for these different mineral phases, and you can see very characteristic jumps here that are mostly related to the phase changes in the minerals. Now, we rarely find, as I already alluded to earlier, with these small amounts of water in minerals, or you know, the water in sediments, we rarely have these pure substances. Yeah? So usually we have some earth materials that is a mixture of different phases, of different constituents, which means that we need to be able to characterize the bulk conductivity of these multi-phase systems. Though the simplest case is a two-phase system where you might have a solid and you might have a fluid. Yeah? So it could be, again, sediment, it could also be partially molten rock, or it could be, again, mineral with some impurities, such as the ones I showed you previously. And there we have two very useful relations, the so-called Husschen-Strickmann bounds. These are theoretical bounds, and basically by using them, we can bound all possible isotropic models and their conductivity to be within these bounds. Yeah? So what they show is called Husschen-Strickmann upper and lower bounds, so lower and upper bounds, Husschen-Strickmann minus and plus here. And here you will find a few numbers. So you will have this sigma f, which is the conductivity of the fluid here, and this is the conductivity of the solid part, so like mineral, for instance. So they could schematically be illustrated using these diagrams here, where yellow is basically a solid phase and gray is the fluid phase. Yeah. So fluid phase is typically more conductive, more electrically conductive than solid phase. So if you have sand and you have some fluids between the sand grains, then your fluid is the conductor and your sand grains are the resistor. So and then the third parameter here is phi, which is porosity. Yeah? So the porosity then defines how much of this gray area relative to the yellow area you have. And what do you think? Where would conductivity be better, here or here? Where would you have a higher electrical conductivity, here or here? If you think of electrical conductivity as or electric current as drift of charged particles, where would it be easier for these charged particles to go over longer distances? This one, yeah? So basically here, if you imagine that this is fluid and these are some grains, you know, they do not conduct current or conduct just a little bit. And here you have a conductive fluid or some conductive material. It could also be some graphite, you know, stripes or something. Then, of course, like here, your charged particles can move around very easily. And here, unless you grow these circles and they start, you know, touch each other, it would be very difficult for your charges to really make over the long distances. Another very important empirical relation. So these are the theoretical bounds. So any configuration of two-phase systems will be kind of between these two, yeah? And the actual conductivities will be expressed here as a function of fluid, solid, and porosity. Good. And then another empiric relation is the so-called Archie's law, which is somewhere between these two. Yeah? But it's a very useful empiric relation because it describes the conductivity of many useful two-phase systems, or many common two-phase systems in the solid Earth. So again, yeah, that's an empirical formulation that works really well for water-saturated sediments and fractured igneous rocks, and it looks much simpler than these bounds. And again, you have solid conductivity, fluid conductivity, porosity, phi between 0 and 1, and this factor m. And m is the so-called formation factor that determines sort of how much how well connected the conductive phase is. Yeah? So if you have m1, then again, porosity is number between 0 and 1. So the best you can have is 1 here. That would just sort of give you the porosity as it is, and you would scale this. Yeah? But as you start increasing this, then something that is less than 1 to the power of larger than 1 will give you a smaller number. Yeah? So if you have m 1.0, then you actually have exactly Hushen-Strickman upper bound. So it's a perfectly interconnected network of this conductive material. So something like that here. And as you start increasing it, so you will get sort of less and less of this conductive phase, and so the conductivity, the bulk conductivity, will be smaller and smaller. And I think it's a good. I think we need M17.3 today. That'll be our perfect match in the afternoon. Yeah, we need this crystal mush whose conductivity could be described by using M1.73. So this is actually an example. So if you have a fluid volume here, fluid volume fraction, so no fluid, all fluid, and this is then the bulk conductivity. And imagine that we have matrix conductivity here. So matrix means solid conductivity, and then the fluid conductivity, which is much higher. So conductive fluid, less conductive matrix. Then as we add more and more fluid, and we have here this Hushen-Strickman bound, lower bound and upper bound, and Archie's curve with two different m factors. And you can see here that if you have upper bound, that means your conductive phase forms an interconnected network. Then even a little bit of fluid in this two-phase system, this is a log scale, will enhance your conductivity a lot. Yeah? So if you add just 10% of fluid into this two-phase system, you increase conductivity by an order of magnitude or even more. And that's why electrical conductivity is so useful for detecting even small amounts of fluid, because fluid is usually more conductive than rock. You add a little bit of fluid, you enhance your electrical conductivity. Whereas if your network of pores is not connected, that would be described by this Hutchins-Wickman lower bound, you see that the conductivity grows much, much slower until certain point, like around 0.8, 0.9, and that's basically the point where these circles, these gray circles, you add more fluid, they grow, and at some point they just start like a good Swiss cheese, like it forms just interconnected pores, And at this point, of course, your conductivity is very good because, again, your charges can freely move around. And this is, why all this is useful, because that's what happens. That's what happens in the subsurface. This is an example of partially molten material. So these are just solid grains, with some pockets of melt, not interconnected. But there are also this path here. This is melt. This is partially molten material at some high temperature, high pressure. And you see that, that you can describe this kind of network using the Hutchins-Wickman bounds. So they're very good for describing the bulk conductivity of these two-phase systems. So yeah, this is some silicate SO2 material, and the no-melt silicate would have this conductivity as a function of temperature. So it grows with temperature, but very slowly, because you need high temperature to start freeing those charged particles, those electrons, and you get a bit of them. But if you add a little bit of melt to it, you see your conductivity starts jumping more and more and more and more and more. So you melt it more, and you have huge enhancement in conductivity. In the interest of time, I'll skip the clay-bearing minerals, which you can check yourself. They are kind of special. They have special conduction mechanism or some peculiarities when it comes to conductivity of clays. And I'll go to the magnetotelluric methods. So before lunch, we will cover just some 1D magnetotellurics. Then we will do practical, very quick one, just to kind of more illustrate you this online tutorial, and you can do more later yourself. And in the afternoon, or let's see how far we manage. So, magnetotelluric method. So, in a nutshell, like for any other electromagnetic method, we would measure magnetic fields, but we would also measure electric fields on the surface. So, a typical setup for a magnetotelluric station would be 3 induction coils two oriented horizontally, normally to the north and east, for instance, and the one sort of vertical coil, and two kind of electrode lines, or 2 lines with electrodes at the end, again oriented east-west and south-north, where we would measure the potential difference, which we can convert by dividing by the length. We can convert this potential difference to the electric field. Yeah, so if we measure voltage here, we get in volts. We divide it by length, we get volts per meter. Volts per meter is electric field. So we would measure 2 horizontal electric field components and 3 components of the magnetic field. This would give us some time series, which we would process to obtain the so-called magnetotelluric responses, or magnetotelluric transfer functions, which we can invert for the distribution of electrical conductivity in the subsurface. So let's go back to the Maxwell's equations and derive the so-called plane wave approximation, which is central to the magnetotelluric method. So we start again with this Faraday's and Ampere's law, and we would need to take the curl of the Faraday's law and substitute the Ampere's law. I'll let you do this yourself. But in the end, you'll get this equation. And we also can assume that conductivity and magnetic permittivity, permeability do not change in time, so we can take these two constants out of the bracket. And we can further use this vector identity, where double curl of a vector field is the gradient of the divergence of electric field, and this Laplacian of the electric field. So nabla squared is the Laplacian. We also assume that our region where we apply this is free of charge. So if it's free of charge, it's divergence free. And in that case, this term is 0, and we are only left with this term. So the equation from this one, we get this equation, which is a second order partial differential equation. And basically, it has two terms. Yeah, on the left-hand side, we have a second order special derivative, and on the right-hand side, we have first order time derivative, or the so-called diffusion term. I believe yesterday you must have learned about it a little bit. So again, we apply the Fourier transform because it's more convenient for us to work in frequency domain, in which case we obtain this equation at the bottom. And for now, we just assume the simplest subsurface model. So we say that we have an air, which is an insulator, and we have an earth, a homogeneous earth that extends to the infinity, left and right and bottom. So homogeneous half space with a conductivity larger than 0. Yeah, by the way, this is the Helmholtz equation. Yeah, so in this form, this type of partial differential equation is referred to as Helmholtz equation. Now we do the following assumption. We assume that electric field is a plane wave. Yeah, so plane wave means it's a homogeneous everywhere. It's homogeneous laterally, and it propagates vertically. Yeah. In which case, in this spatial derivative term, we can basically we have these terms, the derivatives of Ex, and with respect to x and y are 0, and this leads us to the following simplified form of this equation, where we only have a change of E field with respect to the vertical coordinate. Yeah, because this is shown here. So if we have x, y, and this is z axis, so you would need to rotate it 90 degrees to sort of have z going downwards. Yeah. And this is a very simple partial differential equation which has a general solution given here. So Es is the magnitude of the field at the surface multiplied by e to the power of I k z. K is this constant here, called sometimes diffusion constant, propagation constant, yeah. And z is depth, yeah. So yeah, here is an example. E is a plane wave polarized in x direction that propagates along the z-axis. And then any time varying electric field or magnetic field, I mean, any time varying electric field, oh, it's more advanced than I thought, so I could have drawn here, okay. Has a magnetic field. So magnetic field is always there. If there is time varying magnetic field, there is electric field, and vice versa. Yeah? So they always come in pair. But this example here doesn't show two important things. So it shows the propagation of electric and magnetic fields in a very in an insulating environment. Yeah. So they propagate without any attenuation, without any phase shift relative to each other. So that would be more characteristic to the propagation in a very, very resistive environment. What we have in the Earth, we have a conductive environment, we have a non-zero conductivity, and then the propagation of the E field would look more like that. So it would still be this kind of oscillation, but it would decay with depth, yeah, following this skin depth effect that we have looked, so it will attenuate. And the B field will also attenuate, but more importantly, that's important, so there's attenuation with depth, and there is also phase shift, so E and H fields or B fields, they'll be phase shifted relative to each other. So if we assume now that, that this was our general solution, we can decompose it further into two terms here. So we have a surface amplitude, we have a sinusoidal depth dependence, and we have exponential decay with depth. So that basically describes this propagation here. And this constant here that characterizes the sinusoidal depth dependence and exponential decay is alpha, and alpha depends on the conductivity. Yeah? So, so you can imagine a little bit here. So if conductivity grows, so it becomes more and more conductive, this becomes larger and larger. So you substitute it here. This is e to the power of minus something that is larger and larger. So overall, you will have smaller and smaller terms. So this is exactly this skin effect. Yeah. So if you have more and more conductive environment, this field will attenuate faster and faster and faster. And the same for the frequency. So if frequency grows, again, this grows, this attenuates faster. So this is very nice illustration, kind of analytical illustration of this skin effect. And related to this skin effect is the so-called skin depth. That's what we very commonly define in electromagnetism as a depth at which the amplitude has decreased from the surface value, at Z0 by a factor of 1 over E. Yeah? So 1 over E, I mean, E is, it's basically that it has retained approximately 30% of its initial magnitude. Yeah, this would be the skin depth, and you can do these substitutions, and you can analytically define what this skin depth is, assuming the homogeneous half space and the frequency omega at which your field varies. So you can analytically derive, and it is given by this expression here, which can be further simplified here. So if this is the skin depth, which is approximately 500 times the square root of resistivity times the period. Yeah? So this is an example here. It's an animation. I'm going to play it. You have a homogeneous half space of the resistivity of 100 ohm meter in both cases. But in one case, you have a frequency of the field is 0.1 hertz, so period of 10 seconds, or frequency 1 hertz, period 1 second. And we can check the propagation of the field or diffusion of the field in these two media. Yeah? So these two curves, they are exactly these terms, e to the power minus alpha z, so they kind of give you an envelope within which this field oscillates. And you see that here it attenuates much faster than here. Yeah. But what is important, of course, is like if it is not a homogeneous half space, if it's something else, if the conductivity changes with depth, it would still be exactly the same physics. And then the key thing is that this one, at this frequency, you will sound only this depth, whereas at this frequency you will sound a much bigger portion of the subsurface. So if you have different frequencies collected all together, they all tell you something about the conductivity at different depth. So that's what enables sounding. Yeah? If you have only one frequency, you're very limited in how much you can say about this. But if you combine all these frequencies, you sound different depths, and you can start differentiating the resistivity as a function of depth by looking how these fields attenuate at different frequencies. So there is an important next concept, which is called the transfer function, yeah, or the plane wave impedance transfer function. So when you measure the fields in practice, you measure electric field, you measure magnetic field, and basically they come from, they're generated by complex processes in ionosphere and in the atmosphere somewhere very, very far away. And to make it more practical, you want to cancel some part of the information that you don't know. You don't know where exactly this lightning occurred or where the irregularity in the ionosphere occurred. You don't know the magnitude of these irregularities at these lightnings. And what you can do, though, you can just take electric field component in the x direction, for instance, in the north direction, and divide it by the y component of the magnetic field. And this ratio is called the impedance. Yeah? Sometimes also, I mean, you can use B instead of H here. That would change the units somewhat, but it's still okay. And for homogeneous half space, if you assume that that these fields are plane wave and the subsurface is homogeneous, you know exactly what electric field and what electric field is and what magnetic field is. And if you divide them, the only term you are left with is this term here. And it can be written, so the ratio of these fields, the impedance, can be written as this. And you can see here, what's important here is that impedance depends on the frequency omega, and it depends on the conductivity of the subsurface. It does not depend on the surface amplitude of the field. Yeah, so this surface amplitude here cancels out, and that's what you don't know often in practice. And what you are only left with is the sensitivity to the conductivity. So impedance in frequency is usually expressed in frequency domain, and so it's a complex number. It has real part and imaginary part. So it can also be expressed as a magnitude and the phase angle in the complex plane. And also we can again, writing down this impedance for a homogeneous half space, we can express the resistivity or reciprocal of conductivity using this expression here. So you see that basically by knowing the impedance, you can obtain the resistivity. And you will also, I'm not showing it here, but for a homogeneous half space, the phase of the impedance will always be 45 degrees. So we can summarize it all. We have our Maxwell's equations here. We assume the plane wave field, and for now we also assume a 1D subsurface, so the conductivity changes only with the z variable, so only with depth. If you substitute all these assumptions on the plane wave field, on the conductivity changing only with depth, we can simplify these equations into these equations, and yeah, you will have horizontal components, Ex, and the related component Hy, and Hx and the related component Ey, and the vertical field components will be 0 in this medium, so there is nothing that can generate vertical magnetic field or vertical electric field in a 1D environment. And so you can express then the relation between horizontal electric and horizontal magnetic components using this impedance. Yeah, so that the E is related to Ex is related to Hy through the corresponding impedance, and Ey is related to Hx through this impedance. For 1D medium, they are exactly the same, just with the opposite sign. So last slide before we go to the practical. For 1D, again, medium, impedance is the ratio of electric to magnetic field, and it can be expressed using, alternatively, it can be expressed using apparent resistivity and phase. Impedance itself is a function of frequency and subsurface conductivity. And yeah, I mean, this is basically a summary of what I've just said. But the kind of the most impressive thing is that you can actually see it in the data. So you can see in the data, so these are the time series of horizontal electric field components and horizontal electric field components measured at some location in US, I believe. And, but I'm not sure actually, I'd need to check this reference here. And you can see here that how do I? Oh, that's very good. So, and you can see here actually that EY is anti-correlated with HX. Yeah. So you can see that. Wait, EY, yes, EY, HX. Yeah, where you have sort of down, you have up, and where you have up, you have down. And EX is correlated with HY. So, yeah, again. And there is some phase shift, again, because the conductivity of the subsurface is not zero, so we have seen that there is some phase shift between electric and magnetic field. So this basically illustrates that there is this relation between electric and magnetic field components, and analytically it can be expressed using the impedance. So what we will do in this practical now, we will have some Python widget which will allow us to calculate the impedance for a 1D model of the subsurface. So, for instance, where we have resistivity on the x-axis and depth on the y-axis. So this is the homogeneous model of 100 ohm meters, and this widget will calculate the impedance, and it will express it as apparent resistivity and phase curves. Apparent resistivity in ohms per meter and phase in degrees as a function of period of frequency, for that matter. And in case of the homogeneous half space, the apparent resistivity is actually the true resistivity. Yeah? So apparent resistivity 100, so it's 100 at all periods, and phase is always 45 degrees. That's what we have also established. But if we start changing the conductivity as a function of depth, then these apparent resistivity curves and phase curves, they'll not be straight lines, but they will start to vary with period. Yeah, so here you see that up to a certain point, our resistivity, it's actually 10 to 1, so it's 10. It's a resistivity of this layer, and then it jumps from 10 ohm meters to 100 ohm meters at the depth of 10 kilometers. So first it will follow this straight line at the 10 ohm meters, representing basically sounding the first layer with a phase of the 45 degrees. But at certain period, as the skin depth grows with period, and as your fields diffuse deeper and deeper and deeper, you will start sensing this layer here. So the resistivity will grow to, and eventually it will reach a value of 100, okay? And the phase also changes. We can take the opposite scenario. We can take a more resistive layer followed by by a less resistive layer, so more conductive layer. This will be a very different, this will give us very different curves in apparent resistivity and phase. Yeah? So first we will have this 1000 representing this first layer, dropping eventually to approximately 100 representing this layer. Again, these apparent resistivities and phases are computed from the impedance just using this expression here. Can someone explain why is the response of a conductor under resistor is seen earlier than that of a resistor under conductor? So this is so here we see the response already at a period of 1 second, and here we see it. Where is it? Yeah, and here we only start seeing it at a period of 10 seconds or so. So why is that?
Can you repeat the question?
Sorry? So, okay, sorry, here, you see here that this curve is at the value of 10 ohm meters, and then at some point it starts to deviate and go to the value of 100 ohm meters, representing this second layer. And it happens approximately at the period of 10 seconds here, okay? And the same for the phase. But if you flip the situation, so here we have more conductive layer followed by more resistive layer. And we see the changes, we start seeing changes here. Here we have exactly the opposite situation. We have a more resistive layer followed by a less resistive layer. And we start seeing these differences much, much earlier. So we already see the difference here. Why is that?
Is it the attenuation?
Yeah, exactly. Yeah. Okay, good, good, good. Exactly, yeah. So here the attenuation is much less because it's more resistive layer, less conductive layer. So the skin depth is larger, and the attenuation is less. So that's why we see it. This is a very interesting scenario here. So we have a homogeneous model, and then we might have a more conductive layer, thin layer at different depth. And these are the corresponding curves. So you see that that the response of the that MT is basically sensitive to the depth of a conductive layer. So you see that here the blue curve. You start seeing differences earlier, and as your conductive layer becomes deeper and deeper, you see the differences start to occur later and later, with respect to the period. So we can detect these different layers, but you see that the response of the deep layers is much smaller. So for the blue layer, which is this shallowest one, we have a biggest response, yeah, in magnitude. But for this, as the layers go deeper and deeper, the response becomes smaller and smaller. So it's more difficult to detect the deep layers. Yeah, okay, there are other few things, but I guess in the interest of time, we will switch now to the practical, and we might cover some of this by simply doing it ourselves. So, Ashley? Can you help me now?
If you'll go back to the website we were looking at before, the book.magnetic.org, there is another section in there called EM induction. Maybe zoom in a bit. Remember how to get to this website? Down here, there's EM geoscience apps. Okay. And from there, if you click on the yellow bit, and you'll see a link here. So we'll just leave that up for a minute.
Leave it up.
That,
Wait, I need to, you know what I do? I need to duplicate my screen. Yeah, okay.
Just leave that page open just
Yeah.
for a minute or so, just so people can actually get. Has anyone not found that yet?
Connecting to the internet.
Oh. So when you're on this page, click on the title here,
Yeah.
The conductivity properties of like temperature or pressure you showed in the slide was obtained from the experiment.
Yeah. Which one?
Yeah, anything. Like temperatures or pressure.
I mean, like some of these curves, or like this curve. Yeah. I mean, this is experiment. Yeah. So it's a diamond anvil experiment. So high pressure.
Theoretical models.
There are also ab initio, some ab initio simulations. Good question. I mean, there are not that many of them really, so we usually have not enough of them to choose from. Yeah, then yeah, we try to use different ones. Yeah, what we determine geophysically, we determine the distribution of conductivity in the subsurface, and then we try to find an experimental, data that could explain the geophysical geophysical model of electrical conductivity. So if we think that, if there is some water in the mantle, we would use like hydrous olivine model, like the one here, for instance, and try to find a concentration of water based on the geophysical evidence. So different models, yeah, for different scenarios. Yeah. Sorry, are we ready with this?
So has everyone got this notebook open now?
Okay, then we click run all cells. Have you run all cells? Then do you see this this widget, this text fields and bars, or like? Yeah. Okay, so this is a widget that simulates magnetotelluric impedance for a medium with 1 to 3 layers, and the medium is shown here at the bottom. So we have an air here, a layer with air of infinite resistivity, so perfectly insulating atmosphere, which is not, by the way, true. So atmosphere is not perfectly resistive, but that's an assumption within the magnetotellurics. And then we have 3 layers. Each has some constant permittivity, permeability. This is not so important for us now, but it has also this resistivity. Yeah? In the default settings, it's 100 ohm meters for the first layer, 1000 ohm meters for the second, and 10 for the third layer. And on the left, you see impedance, magnetotelluric, so plane wave impedance, calculated at the surface and plotted as a function of period in form of apparent resistivity and phase. Okay? And a nice thing, I mean, maybe we can reduce the frequency range a little bit, because otherwise it's just a bit. So if you change something, I don't know, I click enter, then it's supposed to update. It's unfortunately it's quite difficult to fit everything to one screen, but let's try. Okay. So frequencies go from 10,000 hertz to 10,000 seconds, so 10 to minus 4 hertz. And for now, let's just set set resistivities of all layers to the same value, so like 100. So what happens is that apparent resistivity and phase of magnetotelluric impedance are just constant because we just got a homogeneous half-space model with apparent resistivity that is exactly equal to the true resistivity and the phase of 45 degrees. The other interesting thing, and that relates to one of these animations I showed you with the diffusion of the field, is to click these plot envelope fields. Then it will take some time, and you see it will show you the amplitude of the magnetic field with red, this transparent red envelope, and blue is the amplitude of the electric field in volts per meter and amperes per meter for H field. And you can see, I mean, pretty big envelope in the air, and then you can see how it's not so good really. You know what we can do? Let's change it to 1000 for all. Then the skin depth will be larger, and we will better see this. Yeah, exactly, yeah? So now we see this kind of, this envelope, so how field attenuates exponentially within the conductive environment in the subsurface. This is not correct. Something is not correct. I have to still, okay. Let's just, yeah, exactly. Now this is a straight line, so it's 1000, 1000, 1000. Exactly, yeah, straight line. So let's just try to repeat some of these experiments. So let's make first layer 10 times more conductive, so 10 times less resistive. And yeah, we will see this curve. So where initially for high frequencies, we are fully within this first layer of 100 ohm meters. Our apparent resistivity reflects this value, the resistivity value within this layer. Phase is 45 degrees. And then at some point, it starts growing and it reaches the value of 1000 at longer periods where where fields manage to reach these deeper layers. Okay, let's now do the opposite. So reduce the resistivity of the two deeper layers and leave the resistivity of the upper layer higher. Yeah, and we get the exact kind of opposite. So we have resistive, apparent resistivity of the first layer for high frequencies, and then we go to the lower frequencies, to the lower frequencies, and the fields penetrate deeper and reflect the resistivity of these deeper layers. Yeah, I mean, now you can get creative. I don't know, you can try different things. You can try to sandwich something very resistive in between those layers. So you see we have a very, very conductive layer between two resistive layers. So, and again, you kind of see it, yeah, at high frequencies you are within the first layer, then the apparent resistivity is 1000, then it starts dropping very quickly and almost reaches a value of 1 ohm meter at 10 hertz, or no, at 0.1 hertz, and then goes back to something resistive. So, and phase also changes. When you have a more conductive layer, phase grows, then followed by a more resistive layer, phase drops. Okay, I think, what else can we do here? We can also change the thickness of this first layer. Let's change the thickness to, I don't know, 3 kilometers. What do you think will happen if I change the thickness of this first layer? What will happen to this curve? I change the thickness of the first layer. Yeah, I will, Okay, yeah, it will shift. Well, let's see if it does. Yeah, so it starts shifting to the lower frequencies because it takes time, or because of the skin depth. Yeah, so you need longer period variations to go through this first, now much thicker layer and reach the underlying layers. So I guess you can play with it later yourself and just check your kind of intuition and your understanding of this 1D magnetotelluric impedance. What I wanted to do now, I wanted to also make you aware that this widget is a part of a much bigger collection of widgets and resources on this geosci.xyz. And so if you go to this first link, so if you go back to this magnetic Earth notebook and you click on this em.geosci.xyz, you'll end up on this website where you have some information on the Maxwell's equations, on conductivity, and etc. And here you can scroll down to this button, launch binder. Is it too small? And it will launch this index notebook, which has a lot of such very insightful widgets, mostly on near surface and applied geophysics methods. So doesn't cover the deep electromagnetic sounding or other aspects, but it covers a lot of other things, and I just want to make you aware of this resource, which is also, if some of you end up teaching, you will probably also find it useful as a material for practicals. Okay, I think we are 5 minutes away from lunch. My understanding is this. And I have just one wrap-up slide, which I want to go through together. And there was a recap, because I thought I'll make it after lunch, but yeah, let's make it a summary before lunch. Yeah? So, in summary, magnetotellurics is in 1D is the following, or not necessarily in 1D, but I guess, yeah. Let's see how much of this is 1D only. So we work under the quasi-static approximation that's universal for pretty much all electromagnetic induction methods. In the magnetotellurics, the primary field is assumed to be a vertically incident plane wave that is generated by natural variations of electric current sources that are far away. So these are atmospheric phenomena, lightnings, or some ionospheric irregularities, polar electrojets, auroral electrojets. So something that is far away. And this plane wave assumption holds only within a certain period band. In particular, for Earth, this is typically this band, so this range of frequencies where you can assume that the natural variations you are measuring at the surface, the natural variations of the magnetic and electric fields, they are due to the plane wave source. This is a valid assumption in this frequency range, which enables then all this plane wave impedance and all this other formalism that we have adopted. The depth of penetration of the plane wave field in a homogeneous medium is characterized by the skin depth that is proportional to the period of variation and resistivity of the subsurface, yeah, with this very simple, easy to memorize relation. And then the key concept in magnetotellurics is the concept of transfer function. A transfer function is in case of magnetotellurics, is an impedance that relates electric field to the magnetic field, and is a function of frequency. And if we estimate impedances at a range of frequencies, it allows us to do the sounding. It allows us to differentiate electrical conductivity as a function of depth, again, due to this skin depth effect, due to the fact that fields at different periods attenuate differently. We can start differentiating the conductivity as a function of depth. Yeah, and that the impedance is a complex valued number. It's often represented using apparent resistivity and phase. Okay, I think, any questions? Okay, I hope lunch helped a little bit, so you're ready for the last piece of this marathon, you know, that you've been having this week. So we covered sort of basic things, yeah? The electromagnetic environment around Earth, which provides the source of these natural variations that we use to probe electrical conductivity. We talked about electrical conductivity as a physical property, about electromagnetic phenomenon, Maxwell's equations, Faraday's law, Ampere's law, etc. And then we kind of went to some more specific things. So far, we talked about magnetotelluric method, yeah, which uses part of this natural electromagnetic spectrum where plane wave approximation is a kind of is a valid approximation, and it probes it allows us to sound electrical conductivity in the subsurface. And we looked at the 1D formalism, so the magnetotellurics in the assumption that Earth's conductivity varies only as a function of depth. And what I have as a following few slides are generalizations of the magnetotellurics to 2D and 3D scenarios, so where conductivity is not only a function of depth, but it also varies laterally, yeah? So that there are lateral variations in conductivity, such as, for instance, shown here, where we have a 2D scenario, so we assume that conductivity varies as a function of two space variables. In this case, it will be z, vertical, and y, one of the horizontal directions. And in fact, I think I'm gonna skip this, because in a way, it's while it's certainly not the same as 1D, and there are certain specifics to it. It's very similar in the conceptual terms, these generalizations, and B, they are covered very well in many literature sources, and also in this GeoSci, for instance, web resource. So it's a well-covered field, and I would say that rather than losing you in the forest of these sort of more lengthy equations, we move forward with other topics which are not as well covered in the literature, and I would rather want to show you these results. So these are a few slides on 2D magnetotellurics and 3D magnetotellurics, which I am skipping, yeah? So, but of course you are welcome to check them afterwards, and they'll be there in this PDF. So I'll go to the electromagnetic induction in a sphere. So as you go in this natural electromagnetic spectrum towards longer periods, you increase the depth of penetration because the skin depth becomes larger, but then also naturally the scale of the sources that you have and the spherical shape of the Earth itself become important, and you need to formulate the problem without resorting to this plane wave approximation. You need to work with a sphere, and you need to solve the equations in a sphere and beware of the specifics of electromagnetic induction in a sphere. And one thing that makes it nice is because it boils down to also this potential field representation that you have looked at with Chris yesterday, to the spherical harmonic functions, and you will find, I think, a lot of this material here relatable to what you've seen. But again, our starting point are these are Maxwell's equations in quasi-static approximation, so 1 and 2 here. And if we are at the surface of the Earth or somewhere above the Earth, where we have no electrical conductivity or negligible electrical conductivity, and we have no electric charges or electric currents flowing, then the electric conductivity is 0 and there are no sources, so this whole right-hand side is 0, and we have a curl-free field. So we have the Faraday's law, the Ampere's law degenerates into this equation here. And we can then represent this vector field as a gradient of a scalar potential, recalling also the fact that the curl of any gradient of any scalar potential is 0. So I don't know how Chris referred to it, but it's usually referred as a magnetic scalar potential or Laplace potential. Yeah? So it's just some scalar potential, and the magnetic field is the negative gradient of this potential. So again, this is a valid representation of the time-varying field in regions with no electric charges and no electric sources or electric current sources. Yeah? Okay, so we have this representation, and we also have this equation, yeah, from one of the Maxwell's equations, which states that the divergence of the magnetic field is 0. So there are no sinks or point sinks or sources of the magnetic field, which also means that magnetic field lines, they must close somewhere. You know, if you have a magnetic field line, it begins somewhere and it must close somewhere. Again, this allows us, so if we take now 4 and we substitute it into 5, we will get the divergence of the gradient of V equals 0. And divergence of the gradient is actually a Laplace operator, yeah? The Laplacian. So we can formulate then that the scalar potential is given by solving this Laplace equation. So nabla squared V equals 0. And the solution of this Laplace equation in spherical geometry has been elaborated by Gauss, and it can be represented as a series of spherical harmonic functions scaled by 2 sets of spherical harmonic coefficients, epsilon and iota, of some spherical harmonic degree n and order m. Sometimes we use L for spherical harmonic degree. Yeah? So we have these 2 sets of coefficients, and again, we are talking about time-varying magnetic fields. So it's a function of a frequency in this particular case. So it's a function of space with these 3 coordinates representing spherical coordinates, radius, co-latitude, and then longitude, and then A being the mean Earth radius, so a sphere radius representing mean Earth radius, and then these spherical harmonic coefficients are also then functions of omega. Yeah, and this double sum stated here is typically written as this, or for brevity, I'll be using this notation. So this sum nm represents a sum over m minus 1 to 1 n equals 1 to infinity. By the way, the fact that it starts from n1 is exactly because of this condition. Because if it were to start from n0, it would represent a point, it would represent a magnetic monopole with magnetic field lines extending from the center to the infinity. And that would violate this condition. So that's why this sum starts from 1. Right, so yeah, exactly. So I already talked you through this definition. So yeah, maybe it's only worth to mention here that perhaps what you have seen yesterday was this representation using real spherical harmonic functions. Here I'm using complex spherical harmonics. So, but they are equivalent. They are equivalent formulations. So you can represent them using two real valued coefficients for describing cosine and sine terms, or by virtue of this Euler identity, you can also work with complex valued coefficients and complex valued spherical harmonic functions. So two are in fact absolutely equivalent. Yeah, this is our coordinate system. Exactly, and these are two sets of coefficients. Each is a function of degree n and order m, and in case of the external field, it's a function of frequency, so it's some external field that oscillates at a particular angular frequency omega, and it induces internal field at the same frequency, but the internal coefficients are also a function of electrical conductivity. Yeah? So also see here that the internal field, so the internal coefficients that describe internal induced coefficients due to electromagnetic induction in Earth, they also depend on conductivity. Yeah? Because the induced response, as we have learned, depends on the electrical conductivity distribution. Okay, exactly. So then, basically, unfortunately, as you proceed, these equations become a bit lengthy and sort of complicated, or it might take some time to really adjust your kind of eye to them. But what we do here is that we have this scalar potential, which depends on a position in space, given in spherical coordinates, and on the frequency, and then we take the gradient of this expression, we take the gradient in spherical coordinates, and then we can write the magnetic field components. In particular, I'll be writing the radial component and both horizontal components using this vector representation here. So you can see here we have a radial component where again we have these external coefficients and then internal induced, and coefficients describing internal induced field. And so there's a slide of when you take when you do this differentiation, then there's a change in sign, and sort of you have additional terms here and there, and so these details are important when you really apply this in practice, but for now we are not going to look into this. And these operators here, they are given at the bottom. Okay, so basically this operator, for instance, it represents the horizontal gradient in spherical coordinates, the surface gradient in spherical coordinates. And it's important, again, to realize that the only part in these very lengthy equations that depends on frequency are these coefficients, yeah? the internal and external coefficients. So you can very easily take a backward Fourier transform of these expressions and arrive at a very similarly looking expressions in time domain. So instead of omega, we have t here. and instead of omega here, we have a function of time. So otherwise, everything else is the same. Okay, so this is why it's so powerful, that this representation is so powerful. This is a general representation everywhere outside of this sphere of radius A, in the source-free region, in the current-free region. And if we then go to the surface, so if we start approaching the surface from above, then our R becomes equal to A. So A is the radius of the surface, and R is the distance, radial distance from the center. So as we kind of approaching the surface, R equals A. And these equations here, they simplify a lot. So, and then at the surface, you can write them in the following form. And one thing I'd like to stress here is the fact that how this kind of that the radial component and horizontal components, they have different you see. Let's just look at it. So we have an external coefficient n, spherical harmonic degree n times the external coefficient, and here we have minus n plus 1 times the internal coefficient. And for the horizontal components, we have just a superposition of two. So here we have the difference between external and internal internal is sort of amplified with 1 plus 1 factor in front of it, and here we just have a superposition of external plus internal. So the radial component is somewhat more influenced, or it's easier to see the influence of electromagnetic induction in the radial component because the external and internal contributions, they cancel. Okay, let's now do the same assumption we did for MT. So we assume that conductivity just varies with the radial distance from the center. So that conductivity is a function of radial distance only. So the conductivity is just some 1D conductivity distribution. And we know, from the physics, we know that this external that the external field described by these external coefficients will induce internal field described by these internal coefficients iota. And in a 1D case, this relation is linear, and it's anyway linear even for 3D case, but it's particularly simple for 1D case. This external coefficient of degree and order m is related to the internal coefficient of degree and order nm by this scalar function which we refer to as Q response. This Q response depends on the frequency and on the conductivity, and it does not depend on m order, because our model is purely longitudinally symmetric, so it's just some scalar that depends on frequency and conductivity. Okay. It also is a global response. Yeah. So there is no notion of any coordinate in this equation. So there is no radius, latitude, or longitude. It's just a very general representation between external and internal coefficients. Generally, the more conductive the Earth is, the larger the magnitude of this Q response, and that's also intuitively clear, right? So if it's more conductive, the induction response is larger, so then this Q is also larger. And again, you can very easily, well, maybe less easily in this case, but you can transform this equation into time domain. Just take a backward Fourier transform, and this will allow us to represent this equation in time domain, which has a form of the convolution integral. This is what we call a convolution integral, where we again have this external coefficient, and we have internal coefficient, and then we have this convolution integral that goes from minus infinity in time to the present t. Okay? And that means one interesting thing, by the way. That means that basically the induced response has a memory of everything that has happened in the past that has produced this response. So because it goes all the way to the infinity in time. Of course, I mean, this kernel here, this convolution kernel decays exponentially. So the very long events in the past, they matter less and less. But in principle, this induced response that we measure now has it has a memory about the entire past of the planet. Everything that has ever induced something electromagnetically in the planet will be there, which is just a curious factor which probably has little practical, has few or no practical implications, but it's interesting to think about it. Let's make one further simplification and say that, that Earth is a uniform spherical conductor. So it's just a ball of some electrical conductivity U, sigma uniform. Sigma U, yeah, U for uniform. In this case, you can very easily express this Q response analytically in this closed form, which is just a ratio of two so-called Bessel's functions, yeah? Bessel's functions, which depend on the radius of the sphere, and they depend on this diffusion or propagation constant K, which we already had when we worked with 1D impedance for the plane wave flat Earth approximation. So here is the same constant that depends on the frequency, on electrical conductivity of the sphere. And this, of course, allows us very clearly to see that this Q response that relates external inducing field and internal induced response is a function of frequency and conductivity. So through this and this, which enters these Bessel's functions, we can establish that Q is a function of frequency and electrical conductivity. We can derive further a few asymptotics with this analytical expression. So again, this is our analytic expression. And imagine now that, that the conductivity of this ball goes to infinity, and that the frequency also goes to infinity. So high frequency, high conductivity regime. In this case, the ratio of these two Bessel's functions is equal to -1 or to a unit. And then the Q response is just n over n plus 1, where n is the spherical harmonic degree of the inducing field. Let's now substitute this into the expression for the radial magnetic field component. Remember, this is what we had established for the radial component at the surface of this conductive sphere. So if we now recall that iota and m is related to epsilon and m via this Q response, and we adopt this asymptotic, so we assume the conductivity goes to infinity, frequency goes to infinity, then it's just n divided n over n plus 1 times iota. And that allows us, that basically, like, I don't know, maybe it's not easy to see, but if you take this and you substitute it here, then you will have n plus 1 here in the denominator, and this n plus 1 cancel. And the only thing that you are left is n times epsilon. And here you also have n times epsilon. So it's n times epsilon minus n plus epsilon, so it's 0. So basically what we obtain for this regime where k is much larger than 1, which is this regime, we have established that in this case, radial component must be approaching 0 at the surface of this conductive sphere. And this is a very well known result in physics. Yeah? So it says that radial magnetic field is 0 at the surface of a perfect conductor, so that the field is pushed out from the very good conductor. Yeah? It's not exactly what is happening in superconductors, because in superconductivity is a quantum phenomenon, but the implications are kind of similar. I don't know if you have seen these videos where they have superconductors and some levitating magnets, you know, and there are also concepts like how you make sort of trains, you know, going over these superconducting lines. So it's possible because of this effect, yeah? Because as you approach this regime, the magnetic field is pushed out. So if you put some magnet on top of it, it will never, you know, want to go near this surface. So it's something really, some very deep result that we have just established by looking at this analysis. So it's extremely powerful. But we can also apply it to Earth. So we can imagine that let's say the Earth consists of 2 layers. So the first layer is a perfect electrical insulator, yeah, and the second layer is a perfect electrical conductor. And this is the Earth's surface, and the distance to the perfectly electrically conductive layer is h, or the depth, more precisely, the depth to this perfect electrically conductive layer is h. And we know this. We know that at the surface of a perfect electrical conductor, the radial component must vanish. Therefore, we can write that Br, where we have now substituted the analysis from, I guess I was copying it from, yeah. No, it's okay. So we have elaborated. We have also, we need to go back to this kind of general formulation, and also kind of and also take into account these terms here. Substitute h there, which will allow us to write down the radial component for this model in this form. So where instead of r we have a minus h, sort of the radius of this surface, and this must be equal to 0, yeah, because radial field must vanish. And from that, it follows that this must cancel this. So this difference in the brackets, it must be equal to 0. And the only way to make it work is to make this Q such that these 2 parts cancel each other, in which case Q must be equal to this. Okay? So what this means is that we have just also found another closed form expression for Q in the case of a perfect electrical conductor at depth h. So it's just this. So the Q response of this model is just some real valued scalar. You see that it doesn't depend on frequency anymore. So for any frequency, it doesn't matter. In this case, we will get just a constant Q response. For instance, if you take degree 1 source, so a dipole source, and you take h 600 kilometers, which is the distance to the depth of the lower mantle approximately, that would give you Q 0.37. So that means that the induced response is a 37% of the inducing field, yeah, to comply with the physics of this model. So how does it compare to what we know about electrical conductivity of the subsurface? What I show you here on the left are some electrical conductivity profiles that were obtained from lab-based measurements as well as from geophysical observations, mainly delivered by swarm satellites. So we have derived, and CHAMP, to be fair, CHAMP and swarm satellites. So here we have this conductivity as a function of depth. So this is depth, this is log of conductivity, and you can compare it to this model whether or not you can approximate this as this. I mean, with some imagination, maybe you can, but I would say that's not a good approximation. So what are the methods that allow us to derive such conductivity profiles? You know, how do we get them from magnetic field observations? So obviously, to sound so deep, hundreds and even thousands of kilometers, you need to use some very long period variations. So they are able to penetrate, to diffuse very deep into the subsurface and bring you some information about the conductivity distribution at this depth. And one way to do it is the so-called geomagnetic depth sounding method. Yeah? We will look much more into it when we come to the second practical, where you will basically try to use it yourself for different observatories over the world. But for the lecture, we would like to establish some theoretical foundation for this method. Unfortunately, it means even more equations. Yeah? But we will go quick through them. So to establish this method, we would like to introduce one more concept, one more response function. So we just looked at the impedance response, impedance transfer function. It's also a response function. We looked at the Q response functions, and now we look at the C response functions. So you see, we have the whole alphabet of response functions. So, but that's actually the only other one that we will be looking at in this lecture. You can show, it's a bit of analytical work to do it, but so you take it for granted here. You can show that if you approach the Earth's surface from below, from the direction of conductive spherical body, you can write the radial and horizontal fields not in terms of Q responses as we've done previously, but in terms of these C responses, which is also a function of conductivity and frequency, so very similar to Q response. But these expressions, they have somewhat different form. It's also a double sum. It depends on the external field, of course. And then we have these C responses here. Okay? This C response is, well, that we can skip. Actually, this is also the spherical spectral impedance. So there's also a concept of impedances on a sphere, not only on a plane wave Earth, and C response relates linearly to the spherical impedance. So you see, it's all about the same fundamental physical terms. Let's look a little bit at properties of this so far cryptic C response, and then it'll become clear in the next few minutes. So this C responses is another type of response which is sensitive to the subsurface conductivity, and it's a function of frequency. It has a few important properties. In particular, if you again assume that Earth is 1D, which we do a lot in this lecture, but that's the only kind of reasonable framework for one day kind of EM induction course, because everything becomes much bulkier and complex in 3D. We are just looking at 1D. So real part of this C response, as you will see later yourself, it's a monotonically increasing function with period, and it's a proxy for the EM sounding depth. It means C response has units of meters, and its real part will show you how deep your currents are induced in the subsurface. Yeah, so the real part again tends to a depth of a perfect conductor, because in this case, core can be approximated as a perfect conductor. So the real part of C response can never be larger than the depth to the core. And then the imaginary part tends to 0 as period tends to infinity, and imaginary part does not change sign, so it's always for 1D Earth. Okay, so this is how we can write the magnetic field when we approach the surface from below. Yeah? So that's what this A minus means, so that you're approaching the surface from below, and you can write radial field using these C responses and same spherical harmonic functions, external coefficients. And what we have just established is that if you approach the Earth's surface from above, you can write radial field as this external spherical harmonic coefficients and this Q response. Okay? So these are two equivalent representations that work at the surface, depending on where you approach it from above or from below. And the other thing that we know, or we established, is that as long as our magnetic permeability is constant throughout, and that's what we assume, the radial component is actually, it's a general statement, doesn't relate it to magnetic permeability, that the radial component is continuous across the surface. Yeah? So the radial component must be continuous, and it must be equal to this or this, depending on where you approach it from. That allows us, in order to fulfill these conditions, this must be equal to this. Okay, so you just substitute this to this part, and the second equation to the left-hand side, and they must be equal. That means that these two must be equal, and basically the only way to fulfill this is to make C response related to the Q response in the following way. Yeah, so this is just to show again analytically that C response and Q response are slightly different concepts, but they're related, and they both tell you something about subsurface, about induction response of an electrically conductive Earth. So these C responses is what we estimate in this geomagnetic depth sounding, and we do it in the following way, or at least there's more than one way to do it, but in this case we will do it in the following way. So we will use periods longer than 2 days to sound very deep. And at this period, the majority of the external time varying field is produced by the magnetospheric ring current. We already discussed this a little bit in the first half of the lecture. And this magnetospheric ring current, it's organized primarily with respect to the geometry of the dipole, of the magnetic dipole axis of the Earth. Yeah, so it's not organized in terms of the spin axis, but slightly more tilted, yeah, in this way. So then you imagine there is this current. And which means that if you adopt now this geomagnetic frame reference, then you can describe this magnetospheric ring current to first order by simply using the first zonal harmonic coefficient, so P10. Yeah, so then you would describe sort of, actually it's the other way around, the current flowing in this direction some distance away from the Earth, and it will produce this field, yeah? Which will be a homogeneous planetary field that can also be expressed by the P10 spherical harmonic coefficient. So then, assuming the P10 geometry of the external inducing field in geomagnetic coordinates, and taking magnetic field at some location on the surface, also in geomagnetic, expressed in geomagnetic coordinates, we can write the magnetic field components using these previous expressions in a much simplified way. So basically we are using this somewhat lengthy expression. So if we take just P10, so one harmonic here, and we take R equals to A, then everything is reducing for radial and horizontal components to these two simple equations, which depend on the external coefficient and on this C response and the radius of the Earth and on the geomagnetic latitude. So we can now relate, or we can now divide these two. So just take radial divided by horizontal, and this ratio will give us that, which in turn allows us to express this C response as a ratio of the two magnetic field components, so radial to horizontal, scaled by this term here. And that's basically the practical way of doing geomagnetic depth sounding. So if you measured the magnetic field on the surface, you can Fourier transform it for a set of frequencies, do these Fourier transformations, and take this ratio, and this will give you the C response, which you can use to probe the electrical conductivity of the subsurface. This was first elaborated by Banks in 1969, and is typically referred as a Z/H method, indicating the vertical Z component to ratio of the vertical Z component to the horizontal H component. So again, some practical steps that we will follow later in this tutorial. We can use a time series of radial and horizontal magnetic field components at a global network. That one thing I forgot actually to say is that this approximation of the ring current works well only at the mid latitudes. In the high latitudes, you have other current systems, and you have ionospheric current systems, which will not allow you to adopt this simplistic geometry. So you can only apply this Z/H method to observatories in the mid latitudes. But if we have n such observatories at mid latitudes, we can take the time series of magnetic field measured at this location. We can transform them to Fourier domain, to frequency domain, rotate to geomagnetic coordinates, or first we actually rotate to geomagnetic coordinates, transform to Fourier domain, and then we can estimate this C response at this location. And as a next step, we can try to infer electrical conductivity from these C responses. How do we do that? How do we use these C responses? We know they depend on electrical conductivity of subsurface. That's what we have established from these equations. So how do we get this information back? To do that, we need to solve inverse problem. Yeah. So have you heard of inverse problems? Yeah, you must have heard of inverse problems. Yeah. You mentioned yesterday. Yeah. So we have the following inverse problem to solve if we want to infer electrical conductivity from these C responses. So we have, as observations, we have C responses and some statistically estimated uncertainty of a C response for a set of frequencies. Yeah. This n omega indicates that we have just different frequencies here. And then we want to find an Earth conductivity profile, sigma r, which minimizes the difference between these observationally constrained C responses, and I think this D should not be here. Can I? No, it doesn't work. It doesn't matter. So this D should not be there. So it's just C experimental minus C modeled. Yeah. So we want to minimize this difference and sort of normalize by the uncertainty as a function of sigma. So we plug in sigma here. We try different models of the conductivity and try to find one which allows us to minimize this difference here. And in practice, we need one more term to get a physically plausible sigma. We call it regularization term, which prefers somewhat simpler models among all the models that are possible for conductivity. So in fact, we minimize a sum of two terms, a sum of the misfit function plus some regularization term scaled by this parameter alpha, which we refer to as regularization parameter. So this is a nonlinear inverse problem. It's nonlinear because the C responses depend on conductivity in a nonlinear way. So it's somewhat more difficult to solve than in linear inverse problems you've considered with Chris yesterday, I believe. But nonetheless, it's the same type of problem fundamentally. So it's a nonlinear inverse problem. Given some experimental C responses at a set of frequencies omega, determine or find sigma as a function of depth. So let's look, actually, I'm talking about the C responses. Let's finally look at them. We'll look at them at two locations. So one is in Germany at the Fürstenfeldbruck. Yeah, there's an observatory there. It's in Bavaria, and the other location is here at Hermanus. So, as you remember, I told you we have C response is a complex valued function. It depends on the period, and it has units of meters. Here I just say it's in kilometers, so divided by 1,000. So this is the real part of the C response, and this is the imaginary part of the C response. And you can see that the real part, I mean, with some uncertainty, it wiggles, you know, scatters a little bit, but it's a monotonic function of period, so it grows. And it reaches some values close to 12, 1300 at the period of 90, 100 days. Yeah? And this represents the depth of sounding. It's a proxy for the depth of sounding. So that means that we are studying the currents that are, or we are retrieving currents, or sensing currents that are induced at this depth. Okay, and this is an imaginary part. It's also, it doesn't cross zero, as it should be for a 1D assumption. But now we can look at the one, at the C response at Hermanus. At Hermanus, the C response looks like that, and it violates some of these properties that we have established for 1D responses. So first, the real part is not a monotonic function of period, so it goes down and then it goes up, and then the imaginary part crosses zero, so it doesn't have the same sign. And so this happens because at Hermanus we have a very prominent 3D electromagnetic induction effect due to the ocean. Yeah, so Hermanus is located just at the tip of the southern of the Africa, the southern tip of Africa, and there is very conductive. This is electrical conductance of the ocean and some land sediments. It's in log Siemens, yeah. So it means this is 10,000 Siemens, probably up to 20,000 Siemens. And you can see that there's a very, very prominent electrical, there's a very prominent contrast, lateral contrast in electrical conductivity, and this creates a very prominent 3D electromagnetic induction effect. So at this location, you cannot use this concept of 1D electromagnetic sounding. You actually need to model accurately the 3D electromagnetic induction effect of the ocean. When is the break? At 3:30, yeah. Okay, this is for the geomagnetic depth sounding and electromagnetic induction in the sphere. Next, I'd like to cover this motional induction in Earth oceans very briefly, and then we have our last topic about electromagnetic induction in extraterrestrial bodies. Yeah. Any questions so far?
If there's none from the others, I'll ask you one. This sleep response, so you mentioned that you can use that at mid and low latitudes, but not in the polar region. Do you also have to use night side data? Is SQ relevant here, or
I specifically mentioned that.
C response fine with atmospheric sources.
Exactly. I mean, that's why it's important to consider periods longer than 1 day, where ionospheric signals are very small. Yeah. So and exactly that will be one of the kind of parts of the exercise that what happens to the C response if you go to shorter periods, and I just probably tell you right away that it will give you some very non-physical values of the C response going all over the place, because the assumption about source geometry, that the source geometry can be described by one spherical harmonic coefficient representing ring current, is no longer valid at the shorter periods, because you have ionospheric sources which are much more complex in geometry and would require different approaches. Yeah, good thing about this motional induction is I have very fancy figures to illustrate to you the principle behind this phenomenon. They were prepared by a professional illustrator, by artist. Her name is Lina Jakaitė from Lithuania, and yeah, it was an interesting experience. Like, you will see that it's a relatively complex physical phenomenon, and you need to communicate it to someone who has no background or very little background in physics. She actually has background in geology, which helped. So at least she knew what this is, you know. And then we need to add this physics on top of it, and that was very useful exercise for me, because I could communicate. This also helped me to sharpen my understanding, sharpen the way I can communicate about this phenomenon. So it's in a way similar to this kind of exercise. If you want to make sure that you understand something, try to explain it to 8 years old kid. Right. So first I'll explain you with these illustrations. Then we will look at a couple of equations. So we have magnetic field lines. Yeah, that are mostly due to the field that originates in the core. Yeah, and these are shown here with these thick arrows. And then we have also the ocean. And ocean, as you have seen from the previous slide, ocean is a prominent electrical conductor. So it's relative to the rest of the Earth, except maybe the core and maybe some parts of the lower mantle. Ocean is really the most prominent electrical conductor. But it's not at rest. Ocean is constantly moving. Yeah, there are currents in the oceans, and there are also they have different origin, these currents, and one of the type of currents that we have in the ocean are tides. Yeah, so tidal currents. Actually, these lines here, they are derived from real physical model. This is an IGRF model, field lines, and these flows here represent the flow of the ocean due to the principal lunar tides. Yeah, the main tide that we basically, when we talk about tides, we typically mean this tide that happens twice a day. Yeah, that's quite loud over there. I don't know, we can try to close this window maybe. Yeah, because I try to speak louder and louder, but I feel like I cannot keep up like that for much longer. So we have this main field line, and we have these motions of the salty and electrically conductive water across these field lines. And as you will see later, the electromagnetic induction equations, they predict that if you move conductor across the field lines, you'll generate electric current. Yeah, it's a U cross B sort of term. Yeah, U is the flow, tidal flow U, and B is the magnetic field, generates electric currents which will be perpendicular to both the magnetic field and the flow. And they are shown with this, what is the tile? No, teal color. It's called, I think, teal. I'm not sure. Then these are the electric currents generated within the ocean. You may, again, this is a real physical model kind of projected on this illustration. You can even see that they should correctly follow the right-hand rule, and so this is like that, this is like that. No, this is no, strange. Yeah, no. Anyway, maybe Lina changed that. We will see. Approximately right. Right. And this time varying electric currents, they induce secondary magnetic fields. So by the virtue of the Ampere's law, if you have current, you induce magnetic field, and this magnetic field, I hope this one is right. So this follows the right-hand rule. So this is also simulation result. Okay, yeah. And this would be it if subsurface, if there were only an ocean out there and no conductive subsurface. This would be it. You know, this would be, which is an interesting effect on its own. And that was predicted already by Faraday in the 19th century. But subsurface is also electrically conductive, which means that these fields induced by these flows, they will induce currents in the subsurface again. And these currents in the subsurface will induce their own magnetic fields again. So you see that this kind of chain of events predicted by the electromagnetism, or described by electromagnetism. So the overall situation is much more complicated in a way, and the total field induced by this entire, so yeah, these currents, these represent currents in the subsurface, and then you see that the magnetic field lines, they now have much more difficult behavior, so flowing all over the place. These are again simulation results, should represent some kind of or deliver the real complexity of what is going on there. And the important thing is that when we fly with our magnetic satellites through this magnetic field, on top of many other contributions, we also measure this one. Yeah? And this one is by far not the largest, but it is there in our data. And yeah, and we can use it to probe the electrical conductivity. So let's look a little bit more at how it happens really. So again, I said that the ocean is a prominent conductor because it has you know, a temperature, I mean, that is between 0 and some kind of 30 degrees, perhaps maybe a little more somewhere, depending on the depth. And then it has some non-zero salinity, so there is some mobility of the charged carriers, and there are some charged species in the ocean, and that gives us a non-zero conductivity. Again, this is the image you have seen. This is the electrical conductivity of the seawater as predicted by the equation of state of seawater. So there is an internationally established equation of state. You can give it salinity temperature. It will tell you what the conductivity of the seawater should be. So if we take this salinity and temperature as we have measured them for the ocean, and we convert it into electrical conductivity, and we average out over the depth. So we say that there are some variations with depths, but for now let's not pay attention to them. This is what the electrical conductivity of the ocean would look like on a global scale. And you can see this is a number roughly between 2, maybe a little less Siemens per meter, to 6 Siemens per meter. And you can see some kind of anticipated behavior here. So it's less conductive in the high latitudes because it's colder there, and it's much more conductive overall in the equatorial latitudes, and in some cases where you have very high salinity, such as Mediterranean, Red Sea, or Gulf well, I forgot, the Gulf. Yeah. Thanks. Yeah. Then you have very high conductivity because it's both warm and very saline there. Baltic Sea is, by the way, has very low salinity. That's why it's resistive. Black Sea is the same. Yeah. Sorry.
As an application, the induced current in the sea.
Sorry.
It has an application.
Application.
Yeah, like, I mean, you use for something or you see that in some way, the electric current in the sea.
I mean, we can measure them directly if we place instruments within the ocean, but we indirectly measure them by these magnetic satellites. I'll show you. We see the magnetic signatures induced by this tidal flow, and these magnetic signatures depend on the conductivity of the ocean as well as on the conductivity of the subsurface.
So like some storms, it's more dangerous to be like.
That's an interesting way of thinking. Yeah, well, I don't know. I think it's anyway advisable not to be much out if you have a lightning, especially in the sea. But yeah. So the physical framework here is the following. So we have seen the Ohm's law in a stationary conductor, so where basically conductor is not moving. Yeah, it's some kind of piece of metal or piece of rock. Yeah? And their electric field is related to the current density via electrical conductivity. And here we need to use a more general form because we have ocean that is electrically conductive and it's moving, for instance, due to tides, it's moving with velocity v, in which case we have this expanded kind of Ohm's law where the current density is conductivity times electric field as here, but it also has this additional term V cross B that describes the motionally induced current density. Yeah? And in both cases, this continuity equation applies. I haven't shown it to you. I guess there's some leftovers from other lectures. So we still have our Maxwell's equations as we have seen them. And here, if we want to describe this kind of phenomenon, then within the ocean, where we have the moving conductor, our term J in the Ampere's law will consist of this conduction current and this term here. So if you can imagine if you have magnetic field here and you have the ocean has some non-zero electrical conductivity and it's moving with velocity v, then you will have electric currents induced within the ocean by this U cross B term. Now this B is a total magnetic field, so it includes everything. Just the entire ambient field as you would measure it with a magnetometer. But the largest component of this is coming from the core field. So we can really approximate this B as just B from the core, from IGRF model, for instance. And this would somewhat simplify equations. Okay, so as I said, again, there are different currents that drive the ocean. So there are climatology-induced currents due to wind and some temperature and ocean climatology itself, temperature and salinity gradients. There is Coriolis effect, and then there are gravitational tides, which originate due to the gravitational interaction in the Sun-Earth-Moon system. What is quite interesting is the fact that there are very many different tidal constituents, over 400 tidal constituents, but only few of them occur globally and they have some significant amplitudes. And all of them are sort of periodic phenomena, so with periods ranging from 4 hours to 18 years. So there are if you, for instance, take the real measurements of the water level at one location in Alaska, at the Pacific coast, then this is what the water level will be over, I think, a period of 1 month, approximately, yeah, 1 month exactly. And you can see that this is a superposition of sinusoidal kind of harmonics. Yeah, it has a huge magnitude, over 5 meters at this location, but there are different sinusoidal components to it. The most dominant one is the one that occurs twice a day, and this is the tide as we typically refer to it, this semi-diurnal principal lunar tide. Yeah, and as I said, if you take a Fourier transform of this time series, you will find very clear peaks around periods which are related to the motions in the Sun, Earth, Moon system. So we can express, we know, in fact, we know from satellite data models, we know how oceans move at different tidal frequencies. So we can take one of these models of how oceans move at a particular tidal frequency, like semi-diurnal tide with a period of 12 hours approximately. And we can take the main field model, like IGRF model, and we can just calculate this cross product between them and scale it by the conductivity of the ocean, and that will give us the current density induced within the ocean due to this tidal motion. So we know everything that we need to compute what the current density within the ocean will be, and it's quite complex. Yeah, it's quite complex because these tidal flows themselves are rather complex due to the, because it's not a kind of a homogeneous ocean layer of a constant thickness, but rather we have coastlines, we have bathymetry, and there are some complications. But generally, you will find that and you see that these kind of arrows, they rotate with in this case, the period of M2 tide, so this principal semi-lunar, semi-diurnal lunar tide. So they rotate with a period of 12 hours. And these arrows here, they represent this current density. And they are large, typically where either the magnetic field is, where this cross product is large, which can happen in different kind of configurations, because it's a cross product, so it's the largest when U and B are orthogonal to each other. Yeah, so if your B field is like that and your flow is like that, then the cross product is the largest. But of course, you also need to have some significant B and U. So there is some relation to how large these flows are, how fast these flows are, how large the magnetic field is, and how they are oriented relative to each other.
Sorry, so you say there's effectively no induced field at the equator here in your map?
I mean, not quite, right? Because, well,
Because the field is not vertical enough, or you just said
I mean, there is no current density. Doesn't mean that there's no induced field, because it's
compared to
yes. You can roughly say because U is horizontal. Yeah, at least for the models we use, it's a barotropic model, so it's like U is horizontal always, and B, yeah, that means if U and B are parallel, yeah. But so that means that we can take this current density, we can plug it into our Maxwell's equations here. We can solve these Maxwell's equations and predict what the magnetic field must be, either, for instance, at the sea level or at a satellite amplitude. So this is what you're looking at, is a radial magnetic field at the surface and at an altitude of 430 kilometers, due to the lunar semi-diurnal principal tide, or M2 tide. Yeah, so you see few things. I mean, at the surface of the ocean, you have a lot of details, most of which are kind of also related to the bathymetry of the ocean and some particular geometry of the tidal flow. And a lot of these small details are attenuated as you go to the satellite. You know, all these small details are attenuated, and what you see are only kind of first much smaller in amplitude and second much smoother large-scale fields. I want you to know that this is amplitude in nanotesla, so at most, at satellite amplitude, these fields are at most 2 nanotesla. So this is what we anticipate from simulations. Again, we can, how do we represent these fields in terms of spherical harmonics? So these fields are of internal origin. So if you are at the surface or at satellite, this field originates within the ocean and within the subsurface. So it's a superposition of this ocean field plus the induced component in the mantle. But they are all of internal origin. So we can represent them using the internal harmonic field representation, spherical harmonic field representation, which is already familiar to you. So again, the spherical harmonics, internal coefficients, and some other geometric terms. But we have one more thing to add to this, because we know that these tides have a very particular frequency. So we know exactly what the harmonic behavior of these magnetic fields must be due to these tides, because tides occur with some very specific frequency. So the generated fields must also have this very same frequency. So we can add one more term describing the harmonic behavior in time with the frequency of this particular tidal constituent. And this gives us a very powerful tool, because we can try to look for these particular harmonic fields in the satellite data. Even though these signals are so small, we know precisely what their period must be, and we, on top of that, are quite lucky that not much else is happening at the period of these lunar tides in particular, for instance. At this period of 12 hours, 12.42, and it continues hours, so we know it to the millisecond, you know. So we can just look at this particular time harmonic in our satellite data, and that gives us a chance to extract these tiny signals. And that's what we've been working on. I guess I'll just skip this a little bit, and I want to show you the nice animation which shows the extracted magnetic field, radial magnetic field, at an altitude of, kind of calculated just at an altitude of 430 kilometers due to the semi-diurnal lunar M2 tide. So this is what we see from in the data. We don't use any simulations here. This is simply what data tells us. This is a, you see, this is a repeating field. You know, you see some kind of patterns here, and the period of this signal is exactly 12 hours, 24 minutes, and etc. It's a field with a magnitude between -2 and 2 nanotesla indeed, so very tiny compared to 40, 50, 60,000 nanotesla total field registered by satellite. We are just extracting some tiny bit of it that has this very precise harmonic behavior. Yeah, I'll skip that, and we can do it for other tides. And as we have seen from this very simple sort of illustrations, that the currents that are produced by these tides in the ocean, they generate magnetic fields, and these magnetic fields generate secondary currents and secondary fields in the conductive subsurface. So that means that when we extracted these these tides here, we can expect that some part of this magnetic field behavior is controlled by the electrical conductivity of the subsurface. Yeah, because naturally part of the field is induced in the mantle, and we would like to understand whether we can characterize this part. So the way we do it is the following. So we can solve sort of inverse problem again. So we can say that, okay, this is the ocean, yeah, and this is where these currents are, and then we can say that this is a subsurface which is characterized by only two layers as the simplest possible configuration. First layer represents the lithosphere, yeah, and the second layer represents the asthenosphere. And the depth to this lithosphere-asthenosphere boundary is known from seismic observations, and it's I don't know, how do I denote it? Yeah. So lithosphere-asthenosphere boundary on average is at the depth of 80 kilometers. So lithosphere is a brittle solid layer, and asthenosphere is a ductile layer, and that basically means that our tectonic plates, yeah, they are moving sort of on top of this asthenospheric layer, which kind of serves as some type of lubricant to the lithospheric part of the mantle. Okay, so then we can vary the conductivity of this layer and conductivity of this layer, and for each combination of their conductivities, we can do this simulation with our Maxwell's equation and with this tidally induced source, and we can compute the misfit between simulations and between observations. And for some very particular combination of electrical conductivity of the asthenosphere and electrical conductivity of the lithosphere, you will see that the misfit is the smallest. Yeah? So that means our simulations are closest to our observation around this point, where the conductivity of the lithosphere is very low and conductivity of the asthenosphere is much higher. And this is just to show you this particular point here. So for this particular point, we run the simulation and we can compare it to the observation. And you will see that this is a pure simulation and this is pure observation. And you can see how nicely they correspond to each other. And these values on top of that are very reasonable. So lithosphere is a cold, brittle layer. So we could anticipate it has few mobile charged species within it. So it probably is very resistive. So it has very low conductivity. While asthenosphere is much hotter. It has more mobile charged species. So it's easier for electric current to flow within the asthenosphere because it has higher conductivity. We can also infer the average age of the lithosphere based on that, but I'll skip that part. Yeah, that's it for the motional induction. Any questions?
How we use tsunami to estimate solid structure?
In theory, yes. In theory, yes, and there are many Japanese colleagues who also register, because in principle any flow in the ocean generates some magnetic field signature. It just, with tides, it's the easiest because tides are periodic and very predictable. So that gives us an opportunity to really characterize these signals with very high precision. Tsunamis, on the other hand, are very unpredictable and their special patterns are much more complex. But there are a lot of attempts to use sea bottom magnetometers to detect magnetic signatures of tsunami before they arrive to to the cost, or because the electromagnetic fields, they diffuse faster than the seismic waves travel, for instance, yeah, or the tsunami itself travels. And so there are some attempts to use indeed the sea bottom observations to detect tsunami magnetic signatures, you know, much in advance as possible. Yeah, that's a very good question. Any other questions?
You sort of mentioned it, but what's the longest period tidal signal you can reasonably detect?
Yeah, 26 hours, about 27. It's a Q1 tide. It's a principal lunar diurnal tide.
None of these longer tides and annual variations yet.
I mean, that's an interesting question. We need to look into it, in fact. So we have never like specifically targeted these long period tides. Partly also because, I mean, now we have like long time series, so we can start also looking at expecting these longer period tides. They're much weaker though. They're much weaker than these diurnal band tides.
And is it possible, because there's obviously a 12-hour, exactly 12-hour tide as well, but presumably that's masked by the atmosphere.
Exactly, yes, exactly. So we are targeting lunar tides because they are a bit shifted from diurnal periods. And at diurnal periods, we have ionosphere, which is very, very active, this SQ current system, and polar current systems. Yeah, they completely mask because they're also internal to the satellite, so you end up in this. If we had like on the ground, if we had like a very dense network, you could do this separation because on the ground, ionosphere is external and ocean is internal. But with satellite data, both are internal, so they add up, and the ionosphere is much larger than the oceanic tides. Yeah, we are targeting lunar tides, yeah, because not much happens at these periods other than the ocean. Any other questions? Yeah, right. So we just have this last part, which is induction in extraterrestrial bodies. Yeah, it's a topic that is covered, as I said, by our division, by our IAGA Division 6. And I think it's underrepresented, however, within the IAGA. Yeah? IAGA, at least Division 6, mostly focuses on Earth. And there is this big planetary community that we somehow, over the years, have developed some links to because there are natural synergy between Earth sciences and planetary sciences. And I think this cross-pollination is very useful, and for you as a young, junior scientists and students, planetary sciences is something to keep an eye on because it's a very large and dynamic community with a lot of opportunities. Yeah, so if you have a solid understanding of some parts of Earth sciences, you will, in principle, be able to find your way into planetary sciences if this is something that interests you. But induction, yeah, I will give a very brief overview, and I will focus on the case of subsurface oceans in the Jovian icy moons. Yeah? So the oceans that we think are there under the ice shells of some of the Jupiter moons and other moons, in fact. And I started working on this last bit myself, and I realized that I'm basically repeating a very inspiring review talk on this topic that I listened to some months ago when we organized an outer planet moon magnetosphere interaction workshop at our university. We had Steve Vance from Jet Propulsion Laboratory and Caltech, And he delivered this tutorial talk. So there's also a tradition of having these meetings and tradition of having a few tutorial talks. And he delivered this tutorial talk, and it's such an excellent talk that it has such a very memorable and clear explanations of this phenomena. So I just decided to borrow material from this talk, and I would like to acknowledge Steve. And I have this presentation available, but I was not sure I can share it. So, however, I'm sure if you reach out to Steve, if you get excited about this part, you reach out to Steve, he'll be happy to share it with you, I'm sure. So again, all these slides are on Google Drive, so you can later check out his email. Yeah, in case you haven't known, or you don't know yet, there is a whole variety of what is typically called ocean worlds in the solar system. Probably also outside of solar system, but we don't know really. We think, or there's strong evidence that many of the moons around giant gas giants in the solar system, they host subsurface oceans that are covered, these objects are covered with ice, but we think that for some of these, we think with a higher certainty. For others, we are less certain that they host fluid oceans in their subsurface. And there are several conditions that need to be fulfilled to a certain degree to make sure that the ocean exists and can exist for a long time in these objects, such as, for instance, an ice-covered surface naturally. So if there's an ice-covered surface, there is water, and it potentially can melt. If there is some heat source, it can melt and so become a fluid subsurface ocean. Also, there are some conditions on the geologic structure of these ice shells. In particular, some of these ice shells, they might have some surface features that tell us that this surface ice shell is not like a very static body, but it's an active region that has some faults. And so you see there's a lot of activity going on within this ice shell. And some of these icy moons, they have active plumes. The most famous case is the Enceladus, where the plumes have been observed also in situ with the Cassini mission run by European Space Agency and NASA, I think. Somebody would need to check, was it NASA or the European Space Agency? Yeah. Cassini mission. Anyway, some of you might check Cassini. It was a joint, yeah, exactly, yeah. So it was able to detect and study the composition of these plumes, and and there are other cases such as Triton and perhaps Europa. For Europa, we are not sure. There's some evidence that there might be plumes, but we haven't had a very strong case for Europa. To maintain this ocean in a liquid state, you of course need some internal heating source. And this could be a tidal heating. So if you have eccentric or oblique orbits, then these objects they will experience the tidal deformation, and these gravitationally driven forces and this tidal deformation can be converted into will be converted into heat and sort of heat up the object's interior, or the radiogenic heating could be another way to maintain these oceans in the liquid state. But what concerns the electromagnetic induction, then it's exactly the same principle as for Earth. I mean, as long as we know Maxwell's equations are universal equations, so they hold everywhere, on Earth, but also at other bodies. So we have the Faraday's law of electromagnetic induction, which states that if there is a time-varying magnetic field, then you induce the electric field, and in the case of electrically conductive medium, you would induce also the electric current. So if you now replace this with the Europa, for instance, and you have a time-varying magnetic field around Europa, you induce the currents inside the Europa. So theoretically, again, you can use these currents to study the interior structure of the interior conductivity structure of these icy moons. So what is the source of this time-varying magnetic field around the planets? So in case of the Jupiter, Jupiter has a very strong intrinsic magnetic field that is also predominantly dipolar field, but it has a dipole axis that is tilted by 10 degrees approximately relative to the axis of rotation. So this is actually very similar to Earth. And this is the surface map of the Jovian magnetic field. In units, I'm not sure now which units, to be honest. Yeah, I shouldn't then be, I'm not sure which units, sorry. Then in Uranus, it's also it's the same story. So except that the magnetic field of this planet is not aligned. The best fitting dipolar axis is not aligned with the axis of rotation, so it's actually shifted. So it's not a dipolar field. In fact, it cannot be described only by the spherical harmonic degree 1 coefficients. So, but it's also a magnetic field. The Neptune, yeah, even more exotic in a way, the magnetic field that is tilted 47 degrees relative to the axis of rotation. And Saturn is very peculiar in a way because it has a perfect axisymmetric field. So for the Saturn, the tilt as we know it, as we have constrained it from observations, is, even if it's there, it's less than 1 degree. So it's a perfectly dipolar or axisymmetric field dominated by the dipolar component. So so the other sources, I guess I might have, no, yeah, that's unfortunate. So I think I'm missing one slide. So what is the source? How does this field create a source of time-varying magnetic field at the moon? So imagine that you have moons that sort of rotating around these gas giants. Yeah. So in case of the Jupiter, you have 4 major Galilean moons, so Io, Europa, Ganymede, and Callisto. So these are the biggest moons, and they are located sort of at some distance away from the planet, and they are tidally locked with respect to the Jupiter, so they rotate together with the Jupiter in the ecliptic plane. So they are mostly in the equatorial plane, of the Jupiter. But the magnetic field of the Jupiter is slightly tilted. So as the moons rotate around the Jupiter, in the frame reference of the moon, you will observe the time-varying magnetic field because of this tilt axis of the magnetic field. Yeah, so the moons will rotate around, and they will move through different parts of this main field, experiencing the time variations in the magnetic field. The other 2 major sources of the time-varying magnetic field are again related to the orbital configuration between the host and the moon. For instance, if your orbit is slightly eccentric, that means it's not a perfect circular orbit, but an ellipsoid. Then again, sometimes you're further away, sometimes you're closer to the planet, so you're kind of sampling different part of within the host magnetic field. So at the position of the moon, you will experience some time magnetic field variations. And also inclined orbits, again, so if the orbit is slightly inclined, you'll be flying through different parts of the host magnetic field, experiencing the time variations. So these are some parameters for different moons. So these are, not all of them are Jovian moons, so Mimas, Enceladus, Titan, they are Saturn moons, and Miranda and Triton, I think they're from the blue giants. So you see that they have non-zero eccentricity, and some of them have non-zero or significant inclination. So they would experience the magnetic field variation that are specific to these orbital periods. So this is I have this slide. It's just not where it should have been. This is sort of the magnetic field lines of the Jupiter. So it has intrinsic magnetic field that is dipole dominated, and you see it's slightly tilted relative to the axis of rotation, and it has this sort of also magnetotail, which extends actually thousands of kilometers in thousands of Jupiter radii behind the planet, and in fact we think that it reaches all the way to the Saturn. So Saturn even senses some of the Jovian magnetosphere, we think. Yeah, exactly. And these are four Galilean moons, Io, Europa, Ganymede, and Callisto. I think white is Io, which is missing there. And you can see that sort of as they rotate together with the Jupiter, they are going through this main magnetic field with different configuration. Exactly. This is now the orbit of Europa here in the equatorial plane of the Jupiter. So and this is the magnetic field that sort of spins around. So the next slide. Yeah, I think the next slide shows more or less the same, just from the different perspective. So if you are now at the location of Europa and you record the magnetic field components in this reference frame, so where y orbit is parallel, I think, to the orbital direction, and x points towards the Jupiter, then because of this rotation of the magnetic field and the Jupiter, you will observe these variations at the location of Europa. And this will be the primary driving force of electromagnetic induction at these Jovian moons. Now I think what is shown here is it's just one component of this magnetic field, but there are different harmonic oscillations related to the synodic orbit, to the synodic period, to the orbital period, and they have different magnitudes, as you can see here, but they have very clear periodic characteristics. Yeah, and you see this variation is approximately 400 nanotesla in magnitude in the BX component. Yeah, so it's a pretty big variation, and it occurs every 12 hours approximately, or 11 hours. So the same then, this is for Europa, but the same phenomenon exists at other moons, I mean, there the magnitudes are a bit different, and but the same physical phenomenon in principle. So what happens is that if you have this primary field, sort of that is nearly homogeneous, and it oscillates with this period, with this synodic period of 12.2 hours or 84.5 hours for the orbital period, then you induce the magnetic field in the subsurface, and this induced field will have the direction that is opposing to the inducing field, and so it will modify the total magnetic field at the Europa. So you can see here, I think these field lines are colored by the total magnetic field, and you can see that, yeah, it has different magnitude, and this direction changes depending on where you are along the orbit of the moon. So yeah, changing magnetic fields induce currents in conducting material, and if there is a salty ocean, we know that the seawater on Earth has a conductivity that is much larger than the conductivity of typical rocks, or especially ice. Ice is a very good resistor. So if it is the case, and there is a conducting material, then we can expect a very significant induced magnetic field with the opposing direction to the primary inducing field. Yeah? So as is shown here. So if you apply some field in this direction, so you induce the field in the opposing direction. And this is something that has been observed with the Galileo mission to the Jovian moons. So Galileo was a spacecraft that flew in the 90s, and it made several flybys around the Galilean moons, and it measured the magnetic field around these moons. So it was not in orbit around these moons, so rather it was doing a lot of the flybys. So it was approaching the moon and then sort of going away. And as it was approaching the moon and then going away, it was observed that the field, which is not very well visible here, it was observed that this field has very peculiar structure. So it's not just a dipole field of the Jupiter itself that you observe, which would have been this straight line, but there is this kind of wiggly curve here, and these are the observations. So it has this bump, it has this very peculiar feature. And it was shown that the only way to explain this observation is to assume that there is something very conductive in the subsurface. So there are different sort of models that they try with different conductivity, and I think this solid line here and the dashed line, I think the solid line is a case of a perfect conductor. So something that has a very strong that generates a very strong induction response, and that fits the observations the best. And this was the primary and a very convincing first evidence for an existing subsurface ocean in Europa. There was a very significant discovery back then, and I think the fact that it was done by using electromagnetic induction speaks for the power of this geophysical technique. And it's actually almost a conclusion. So what I wanted to deliver with this is that if you have time-varying magnetic fields around these extraterrestrial objects, you will have a phenomenon of electromagnetic induction. So if you If you can measure magnetic fields there and you know the sources of this time-varying magnetic field or can characterize them somehow, then you can do exactly on induction sounding in a very similar way it's done for Earth and discover something that is very, very unique. And the reason I thought I should really tell you about this again, because your career, you know, if you stay in academia, your career will be in a very unique kind of time period where we will have many missions approaching the Jovian moons. You know, we have had the ESA mission JUICE that was launched just recently, and it's a mission that will go to the Jovian system. It will make a few flybys around Galilean moons and eventually go into an orbit around Ganymede into 2034 or something. And this will be really, really unique opportunity to study, to get new observations from this, about these Galilean moons, including the magnetometer. And then we have a NASA mission, Europa Clipper, that will also go to the Jovian system. It was launched later, but in fact it will arrive a little earlier. And it will mainly target Europa with a few flybys around other Galilean moons. It will mainly study the Europa, and it will also carry a magnetometer. And then there is another mission, NASA Dragonfly. I actually know much less about it, but it targets the Titan, the largest moon of Saturn. And which something that is not on this previous slide is because it's something very recent, is that the ESA has selected Enceladus as a target for their next large space mission, so-called L4 mission. And it's been announced. I think there are some final preparation for the next ministerial meeting that will happen in the autumn, and if funding is approved, then this mission will happen. And it's a very ambitious mission because it, in its maximum kind of capacity, depending, I guess, on the funding and some technological aspects, it will send both a lander and an orbiter to Enceladus. And so, yeah, I guess that's some kind of artistic sketch, and it will make a few flybys, as you see, around other moons, and eventually settle on Enceladus in a kind of orbit around Enceladus, and then maybe lander. And because this payload is so heavy and ESA doesn't have its own large rocket, they will actually launch it. They plan to launch it with 2 rockets, and they'll do what they call rendezvous in space, where the 2 modules will meet in space and combine payload, and it will be transported to the Saturn system. Why Enceladus? Because, as I said, Enceladus has all the evidence that there is subsurface ocean. It has geysers, which we have observed, so that means there is probably some activity. We think that they emitted, from the previous observations, we know that the emitted material is coming from the ocean, not from the ice shell, because it carries particles of silica material, indicating that they come from probably from the core, from the rocky core of Enceladus. So we think that Enceladus is geologically active, potentially with some hydrothermal circulation within its core, and then the ocean and sort of an ice shell. So it has all the so-called habitability factors. So the ultimate goal of this mission is to study the habitability of the Enceladus, whether there is potentially a life, in this ocean, or what would we need to do next to say if there is a life. So this mission, if launched, Yeah, I mean, it depends now on many factors, but it takes many years to simply even fly to this Saturn, so 10 years. So right now they plan that it will arrive to Saturn in 2050 something. So it's a long timeline, but there are many young faces in the audience. Yeah. So it will be your generation. It will be our generation to launch it, and it will be your generation to study this. And with all the other missions, this is a unique opportunity. Yeah. Also for magnetic field studies about you know, not necessarily focusing on Earth, but also for extraterrestrial bodies. So this concludes my lecture, and yeah, the end. Yeah. Actually, not quite. So, not quite. Yes. But thank you for a round of applause. That was that was nice. Yeah. Yeah, we have a second practical, which is a Jupyter notebook, yeah, and it implements this geomagnetic depth sounding method. In particular, the Z over H method, yeah, where we will use ground observations of time series of the magnetic field to sound electrical conductivity of the mantle, using Jupyter and Virus and a couple of other packages. So I guess that one is just, we just go there to the book Magnetic Earth, and let me see. No. So let's open it. Let's quickly go through this notebook together. I just need to get my Wi-Fi back. So we have half an hour, a little less. I don't think you will be able to do the full exercise, but at least let's try and go through it together. Make sure that you can run this whole notebook and then see. Maybe we can play with a few options. Right, so exactly. So it's here on the left, EM induction, deep electromagnetic sounding, using geomagnetic observations. So here, are you able to? Okay, so we need to click on this rocket sign, and then Jupyter Hub. It will launch the server. This time we are operating within the Virus virtual research environment, I believe it's called. So are you able to make to this point? Yeah, okay. Right, so I mean, we don't need to go through this method section again. So it was covered in the lecture. So we are going to estimate this C response from the ratio of the vertical to horizontal components. And for that, we need time series of the magnetic field observations at the Earth's surface, and we are going to get them using the virus client. You have covered this, haven't you?
Yeah.
I mean,
So you can skip.
you'll just skip that, yeah.
Share access.
Okay, okay. So let's just run these cells. No, can we run these cells? Yeah. Let's just run these cells because we need them for what comes later. Yeah, there is a lengthy explanation, or like some explanation what these data collections are and how to retrieve observatory data, but you know this by now. I guess where it starts to be important is that here we plot the map of geomagnetic observatories over the, I don't know, last 12 years, I guess, since the time, oh no, I think it's all observatories over all time. Anyway, I think we have much less presently running, but we don't have to use running observatories. We can use also some archive data, including observatories that are no longer active. Yeah, and then we have this this cell here, which sort of just does some zoom in into the continental Europe region. And the observatory that we will use first is this Fürstenfeldbruck Observatory, which we also covered in the lectures when we discussed these sea responses. So this is observatory in the southern Germany here. So they are named by their corresponding IAGA codes. Yeah. So here we are forming the request to the virus client. So we want to retrieve the hourly mean data for this Fürstenfeldbruck Observatory, and we are retrieving data, I think, 10 years between January 2014 and December 2023. So let's do that. And we should be able to plot these magnetic field components X, Y, Z. Here, I don't know, Ashley, can you maybe walk around and check if are you okay?
Is everyone being
Okay.
yeah.
Right. So that's good. And this is the total field observed at an observatory. And it's, of course, dominated, as we have already discussed, by the core field. Yeah? So the X component, 21,000 nanotesla, Y is very small, and then vertical component is the largest. And so it has these very long-term variations related to the secular variation originating in the core. And that's not what we are using for electromagnetic induction. So we need to subtract the core field from this time series. And to subtract the core field, we request the virus to give us predicted core field at this location over this time, as is given by the comprehensive inversion model. So there is a specific product there. It's called MCO. Yeah. Anyway, it's a quite cryptic names, I appreciate, but that's what it is called. And the other source that we want to subtract are the lithospheric static crustal field. Yeah, so the static component that is due to the local signals caused by the magnetized material in magnetization in the crust. So we will remove this core and crustal field by requesting these models, and then basically we form a new array dB, which is our observations minus core field minus crust field. So very simple at this point. And we will plot them again. And now you see the residuals, yeah, what is left after this subtraction, and you can see that these are, there is no long-term trend anymore, and there are very clear. There are a lot of these spikes which are mostly related to geomagnetic storms, and there are also these annual periods or seasonal periodicity, which is also related to the seasonal variations in the magnetospheric and ionospheric sources. But there is still some constant shift that is due to the fact that our models, they do not perfectly model the local field, so we still have some offset. Yeah, so you see that these time series are not centered around 0. So we will just also subtract just the constant mean value from this time series to make them centered around 0. So finally, these are our residuals centered around 0, and and this is sort of the signal that we can use for induction. So now we assume that everything that is in this time series is caused by, or the magnetic field that we have now left is a superposition of some external magnetic field plus the corresponding induced magnetic field. So this is kind of the foundation for the observational foundation for our induction sounding. As I said, we will use long period variations that are mostly caused by the or generated by the magnetospheric ring current. Ring current organizes itself in the geomagnetic dipole frame. So what we do next, we do the coordinate transformation, where we transform the coordinates of our observatory as well as the vector magnetic field to the geomagnetic dipole frame. And for that purpose, we use this additional package called Dipole by Carl Londal. And it's a very small and nice tool. You can check it later yourself. It has a lot of useful functionality. Among other things, also this transformation. So we basically say that we want to transform, the geomagnetic dipole frame changes with time, because the Earth's magnetic field changes, the dipole component of the Earth's magnetic field also changes. So the frame of reference will change slowly in time. But we just pick one particular time corresponding to the 2015 epoch of the IGRF model, and this is our sort of frame, geomagnetic frame, into which we will project all our data and the location of the observatory. So then we call the corresponding function to do this transformation. If you want to understand exactly what this function, or understand more about the internals of this function, you can call the documentation, and so it will describe the input and output and a bit what it does. And then finally, now we have our magnetic field residuals in the geomagnetic frame. So we can use them to estimate the transfer functions. We need to do it in frequency domain. So when we discuss these Q responses, these transfer functions, we always discuss them in frequency domain. So transfer function, is a concept that in electromagnetic induction is formulated in frequency domain. So we need to do this Fourier transformation to the original time series for some frequencies of interest. If you just pick a few frequencies and you do this Fourier transformation, it will not be enough to derive reliable transfer functions. So rather, what we do, we implement this so-called spectral stacking approach. Yeah? We take our time series and we split them into windows. Yeah? Into some, they might overlap a little bit, they may not overlap, but we split them into some windows, and these windows usually have a length that is corresponding to the length of a period of frequency which we target. So if we have hourly data and we want to estimate transfer function at a period t hours, then we split the hourly mean time series into L windows or equal segments, and each of these window is a realization of the magnetic field. And yeah, each has a length of t samples. Then for each of these realization, we perform the discrete Fourier transform stated here. So we basically take a sum of the actual measured time series with this exponential factor, where exactly this z hat lk is the k denotes the k value in the Lth realization. So we take one particular realization, one particular window, and then we iterate over all samples in this window and multiply them with this exponential factor, and so that's our discrete Fourier transform. And this omega here is just 2 pi over period. Period is given in hours. And then we do this for a given frequency for the vertical component, and then we do the same for the horizontal component. And then we have, how many windows do we have? We have L windows, and after doing this for each window, we will have L such spectral transformations, yeah, for each window, for vertical component and for the horizontal component. And then we can derive we can do this so-called spectral stacking method. So we can derive this ratio between the Z and H components by doing this operation here. So it's a ratio of two dot products or inner products. Here Z times H star, where star means the complex conjugate. So conjugate means you change the sign of the imaginary part. Yeah. So in case of the nominator, we have the inner product between vertical component and horizontal component, and we normalize it with the inner product of the H with H star. So these brackets, they indicate the sum over all realizations, okay? So we just multiply each sample from each time window and we sum them up. As a quality measure of our estimated C-response, we use the so-called squared coherency. So this is just a link to the Wikipedia page, so you can read what coherence in signal processing means. For what is worth for this tutorial, you could imagine it as some quality number. It's a number between 0 and 1, and the high quality transfer function will have a very high coherency close to 1, and the low quality transfer function will have a coherency that is close to 0. So coherency again is calculated using these inner products between different components, as is shown here. We can also estimate the statistical uncertainty of this estimate, of this least squares estimate. I mean, basically what we do in this line here is a least squares method, even though it may not be obvious, but there is some literature at the end. You can later check it and try to to establish the link between this expression and the least squares method. But here, yes, we can estimate the uncertainty of this C response by following this equation here, where basically the uncertainty is going to what do we have here? We have C estimate of the C response itself squared times 1 minus the coherence here, and we have these other terms here, coherence squared, and we have this beta. Beta is the value that is defined as following. So if you take 1 minus beta, then it gives us the probability that the modulus of this C response estimate lies within the error bar with C plus minus delta C. Okay? And you can see the role of coherence a little bit here. So if we have a poor transfer function, so the coherence is close to 0, then basically we have something very small in the denominator. So you will divide something bigger with something that is very small. This will be a bigger number. And this number, if this is small, is close to 0, then this is just 1. Then the uncertainty in the end is very large. If you have a perfect transfer function with coherency of 1, then 1 minus 1 will give you 0. And so in total, you will have uncertainty of 0. So again, this is how coherence also translates to the uncertainty. Yeah, and basically this is the gist of this exercise, is the implementation of this spectral stacking method. It's implemented in this function, so you will maybe need to spend a bit more time on going through this. In case you have questions, I'll be happy to answer it. So, but in principle, it does exactly what these equations state. So we define an exponential factor, and then we transform the data into frequency domain, and then we derive these inner products between different components, and this will give us our transfer function estimation. Then we compute the squared coherence following implementing the formula above, and finally the uncertainty of this estimate. Okay, so once we have done it, we can use this function to estimate transfer function at a set of frequencies or periods. Here we define the range of periods between the shortest period of 48 hours or 2 days and the longest period of 50 days. This we define 16 periods that are uniformly spaced on a log scale. So this function gives you 16 uniformly spaced log-spaced values between the starting period and the maximum period. Then we pass this list of periods together with the residual magnetic field residuals. We pass this to this function that implements this spectral stacking. And okay, something I didn't run, probably this one. Yeah, so we have 16 periods, and you can see that here it does the estimation for all 16 periods, and it reports how many realizations or how many windows we have for each period. So remember, we have 10 years of data, so we have 10 years of time series in this ArrayDB MAC. And you can see that as we go from short period to long period, the time window becomes larger and larger, because it has to be at least as long as the period we estimate our transfer function at. and we have fewer and fewer realizations, fewer and fewer windows. Right. Then we take this spectral ratio of vertical to horizontal component, and we scale it with this A/2 times the tangent of the geomagnetic colatitude. So basically, we are implementing this. Let me find it. Yeah, so this ratio is our, we're estimating it using the spectral stacking, and then we just multiply it by this factor here. And this finally gives us the transfer function, and we do the same for the uncertainty. This gives us the transfer function and its uncertainty, and we can plot this transfer function together with its coherence. So you can see here, this is the real part of this transfer function. This is the imaginary part at the bottom, and here you can sort of go back to this example here, where I showed you the transfer function approximately in the same period range at for the same observatory, and you can cross compare these results a little bit. I mean, there's some variations here, but overall, you should be able to see that they're very similar. Important properties of 1D transfer or transfer function for a 1D model is that the real part is a monotonic function of period, and the imaginary part doesn't cross zero. I mean, with some kind of error bars here, you can imagine this to be the case largely. I mean, you have some scatter. This is not monotonic behavior, of course, but it's also rather simple data processing that we are doing here. This is the coherence. So you see that the coherence is highest at longer periods, in fact. So this means, among other things, not only that the quality of our transfer function and its uncertainty are, or the quality of our transfer function is higher at longer periods, but it also tells us that this P10 approximation that we are adopting in this method holds well for these longer periods, or at least holds better for these longer periods compared to the shorter periods. And the next step is really also implementation of this simple inverse procedure, where we seek a conductivity model that minimizes a data misfit between the observed and modeled responses. So we basically implement this protocol here, trying to find, I mean, all these equations are also repeated here. And so we will try to find a conductivity model that best explains these observations. So phi is our misfit function, or our function, objective function that we try to minimize, that consists of the data misfit term and the regularization term. So again, basically, yeah, phi d plus regularization parameter times phi m, representing the regularization term. We define a very simple subsurface model consisting of only 3 layers to do this inverse problem, and we are doing it in a very inefficient way. So we just do the so-called grid search algorithm. So we are iterating over all possible combinations of conductivity within these 3 layers, which range between 10 to minus 4 Siemens and 10 Siemens on this grid. So within each layer, we will try each of these value of conductivity and calculate this objective function, and then pick one model for which this objective function has the minimum value. It's gonna take a while, so this is where we are iterating over Yeah, and one thing I forgot to mention is that within this procedure, we need a forward operator, right? We need some function that models the C response given the distribution of conductivity, yeah? And this function is called from the chaos magpie Python package, which you might have heard of yesterday. So chaos magpie implements the C response calculation for us, and so we are just calling it from the chaos itself. So we are still iterating over all these combinations, and now we are done. And then we simply results here. They store all the tried models, and we are pulling out a model that has a minimum, a lowest sort of objective function value. And it tells us that this particular model has a conductivity of 0.01 for the top layer, slightly higher conductivity for the second layer, and higher conductivity for the third layer. And we can also compute the responses for this final model and compare the responses of this simple three-layered model with our observations. So these black lines, they are the responses of the model that we found in this inverse problem, and these points here are our observations. So we found a model that fits observations quite well, I would say, given that it's such a simple 3D layer model. And finally, we plot this model here, this orange line, and we can compare it to this more kind of sophisticated conductivity profile that was derived from satellite and observatory data. That's also the one that I showed you during the lecture. So you can see it's not so bad what we have found. Yeah? There are some differences, but overall we found a very physical, reasonable conductivity model under the Furstenfeldbruck observatory that extends all the way into the lower mantle. Yeah, and actually that's it. Yeah, so the exercise that you can try later yourself if you like is to try and vary the regularization parameter, try to estimate this transfer function at shorter, longer periods, and then also try different observatories. You know, you can take a different observatory, Boulder in US, Alice Springs, for instance, in Australia, derive conductivity profiles under these observatories, see how different they are, and what these differences could be caused by. Good, yeah. I let you discover this in your subsequent efforts in this field, which I hope you are motivated to do now. Okay, good. That's it.
Wow. So.
Intense.